Good morning, colleagues. Can you hear me?
Yes, we can.
Good, thank you.
Yes, Prof, we can.
Okay, I'm just going to start by, I just want to show you a couple of, where's my camera? Here we go. I just want to show you a couple of texts that I use a lot for the statistical analysis that we do it's as consultants in StatCon. So one of the texts, this is a text called Medical Statistics by Kirkwood and Stern. It's a very well-known book, which is very good for general statistics. So you get texts which have got different levels of complexity. So it does cover a lot of the statistics that you would use in the medical field or in the science fields, but they're not. It won't cover everything, obviously. This is a very good book called the SPSS Survival Manual by Julie Pallant. There's a number of editions of this book out, and it's a very good general book for if you're going to be doing statistics. It has a number of statistical procedures in it, and then it doesn't cover all the procedures, but it has a very good coverage of the procedures that are in the book. I've got a couple of these books. They're particularly written for SPSS, and there's a number of them, which cover different. Some of them are just general textbooks, and then others are covering specific procedures. So you get sort of a more general kind of text, and then textbooks which cover, or books which cover very specific procedures. If you're doing something more complex like structural equation modeling, then there would be you need to find a text on that particular procedure, because that's normally the general textbooks wouldn't cover something like structural equation modeling. This is for the qualitative people out there, qualitative data analysis. I don't want to leave you out. And then just for supervision, from a supervision perspective, this is a book that I got recently, Evaluating Research. I haven't had time to look at it in detail, but I'll try and extract a couple of chapters for you just to give you an idea of what the content is. But I think if you're supervising, it's good you will be evaluating research as well. And just as an example of that, yesterday I had a meeting with a student from, he's actually a staff member from one of the departments at UJ, and he'd done a proposal. And so, for example, he's new to research, so he's a sort of novice researcher, and he described in his proposal, he'd used the word interpretive for a quantitative study, and that's the wrong kind of terminology. Obviously, interpretivism is more qualitative. And then he'd also described his sample as being inappropriately, because what he's doing is population sampling or total sampling, but he described using a sampling method. So and then his questionnaire was, we did work on his questionnaire yesterday, but we're going to have to meet again to it further. And then this is another book that I recently got, Statistics Done Wrong, where it highlights the problems that you can have with statistics, or where you can misuse statistics. And I've given you a couple of chapters on that, but I'll also get a couple of chapters from here for you to have a look at as well, just to understand when we do statistics, you can use them incorrectly, and that's a problem. Okay, so I'm just going to stop sharing the camera just to save bandwidth. So I'm just going to disappear. Right, and then I'm going to just share the presentation. I'm just going to move these books away. And also just to say that there's a lot of resources online as well. There's some very, very good resources online if you don't want to go to the extent of buying books, for example, because they are very expensive. All right, so today we're going to continue with the data analysis and writing up phase of the research. I just have to apologize again for the delay with providing feedback for assignment 1. I'm not getting to it, but I'm going to set aside time from tomorrow to work on that. Okay, so the main focus today is data analysis and writing up the findings. So we're going to focus on analyzing and interpreting data and then reporting on results. So how do you write up the results so that you can inform others of your research? And just to remind you, these definitions of statistics, one where there's a sort of reference to science and then one where there's a reference to art. So this idea that we kind of doing something scientific, but there's also an art to the process of analyzing data. So some questions that you can ask yourself and also ask your student is, how have you learned about statistics yourself? Do you use statistics in your research? I think some of you do and some of you don't at the moment. What type of statistics have you used so far? That's also an important question for supervision, because if you're supervising students, you need to be able to give them the support that they need if they're using statistical analysis. And if you can't provide the support yourself, then you need to identify somebody who might be able to help them. So that's and I think we sometimes get students coming to us who are using a procedure that the supervisors never used. And we all, even my own experience when I was a student, I would often be using a technique that the supervisor hadn't used before. So you have to then find somebody else who can advise you, or you have to work out how it works yourself. So that's I think where I would be concerned is when if the supervisor doesn't know anything about the issue at all, or the procedure that's being used, and then they can't actually provide much support for the student in terms of the methodology that they're using. That can be a problem. Okay, and then obviously another question is, do your students need statistics for their research? It's a good idea for, I think it's a good idea for anybody to learn different types of methodologies. So I think it's good if you can have experience in quantitative and qualitative research methods. But it also depends on what they're going to be doing in the future. So there's certain disciplines, for example, where particularly the professional disciplines, where the person might never need to run a statistical test again in their life, in which case you have to ask the question, how important would it be for them to know how to run statistics? But it is, I think it's good for everybody to know how to read statistics and how to interpret them, though. Okay, and then the big question for a supervisor is how for a supervisor. Okay, there's a bit of reflection going on there. Okay, that's quite scary. So the question for the supervisor is how do your students learn about statistics that they need to use? And there's some suggestions coming up later on for that. Excuse me. Okay, so the main themes for today will be about different sets of statistics, descriptive, and then we're going to look at descriptive statistics, and then inferential statistics, and then we're going to look at specific tests, parametric tests, and then also non-parametric tests. So we're going to cover quite a lot of ground today, so just to kind of highlight that the main point is to highlight that there's different kinds of statistics that we can use, and to give an idea of when we would use them. So if you are supervising students in terms of a statistical kind of project, a statistical based project, it's to know that there are different options available and when you might need to use them. Okay, so when a student does a quantitative project, they need to report an analysis plan. we get quite alarming analysis plans in proposals. And the reason for that is the students don't often, because they haven't done statistics before, they don't really know what to write there because they haven't had any experience with writing up they don't know, they haven't done the analysis before. And when you haven't done something before, it's difficult to know what to write about it. So these are just some examples from proposals that we've received. So the data will be allocated and divided into specific fields of interest. An Excel spreadsheet will then be designed with the help of StatCon to collect and analyze all fields of interest. So that anything about the variables that's going to be measured, it's just sort of it doesn't have any real value. It's not explaining to the reader what that analysis is going to entail. And then there's another example here where it's focused more on what how this, what this, maybe the software that the student is going to use, and then they're sort of saying that they're going to rely on the consultation service for capturing and analyzing the data. But there's nothing about the variables that are going to be measured for the study, these are examples of poor analysis plans. So the chapter that I always share by Blakey is good because it gives you, the reason why I like that chapter is it gives a link between the research questions and the analysis that's going to be done. So this is an example of a more appropriate analysis. So to answer research question 1 for this particular project, cross-tabulation and non-parametric tests for significance for the variables will be conducted. So it's indicating what particular tests will be conducted, excuse me, on the variables of interest for the study. So you've got a clear idea there what the variables are and what the tests are going to be run on those variables. And then similarly, the association between age and the ordinal interval ratio versions of the 3 environmentally responsible behavior variables will be analyzed where appropriate using the same methods of analysis. So that's telling you what analysis is going to be done to answer research question 1. And then here, for research questions 2 and research questions 3 for this particular study, the age distribution will be tabulated and plotted against the environmental worldview scores and the subscale scores, and these will be presented in tables and graphs and so on. So they're kind of explaining exactly what analysis will take place to answer the questions. And that's the level that should be provided in a proposal. But as I said, the reason why students don't do this is because they haven't done the analysis before usually, and they often don't really explain the variables very well either that they're working with. Analysis plan should include reference to research questions. So it's a sort of a reflection of the research questions and how they will be answered with the analysis. There needs to be a reference to the constructs which are being measured in the study in relation to their type of measurement and how they will be related to each other. And we'll look at examples later on in the session about how you would manifest that. And then there needs to be a reference to the statistical test or tests that are going to be used and how those are going to be used to analyze the construct. So usually you'd be testing a hypothesis, or in that previous example, the analysis was actually mainly descriptive, but you need to indicate what kind of statistical procedures you're going to be using for the study. Excuse me. So how does the student work out what analysis they should include in their plan? So one thing they can do is they can refer to analysis used in existing research publications. So if they're doing something similar to what somebody else has done, they can extract the sort of analysis, the example of the analysis that somebody else has used. Not all studies will be the same, obviously, so you might not be able to sort of translate the analysis exactly as it was, but you should be able to get some ideas about the analysis, the possibilities for analysis. You can also refer to resources which guide us on what statistics to use, and I'll give some examples of those during the session. So you'll see how some of the texts help us with types of statistics that we can use. Then you can also get advice from experts such as the supervisor or a statistical consultant. So, for example, at UJ, students can come to us and get advice on the type of analysis that they might be able to do for their study. We look at the proposal, we look at the type of the design of the study, and then we will give advice on the analysis plan. And then obviously the student can also attend statistical workshops, but it's important to make sure there's a huge range of statistical procedures. So it's important that they make sure that they are attending something which is relevant for their research. So if you need to do a rash analysis for your study, for example, there's no point in going to a structural equation modeling workshop, because that's not going to help you with your rash analysis. Okay, so in terms of sets of statistics, there's lots of statistics that we use, and it can be quite intimidating. But usually when you're doing a project, you're going to just use a small number of the statistics that are available out there. So the idea of this component is just to give you an idea of the range of, or the sort of, there's a huge range of statistics that are available. But remember that you wouldn't need to use all of them, or your student wouldn't need to use all of them for the project that they're working on. So the most basic type of statistics are what we call descriptive stats, and we'll look at those a bit later. There's also statistics that we use to measure normal distribution, and that's an important component for deciding which tests we can use, as you'll see later. There's also statistics for reliability and validity. We mentioned some of those in previous session. So Cronbach alpha, which we use for reliability, and then there's also measures we use for convergent and discriminant validity. There's also what we call data reduction techniques. So, for example, factor analysis is an example of that. So those are procedures that we use for reducing either cases or variables into groupings. And then there's inferential statistics, which are there's a whole range of tests within inferential statistics. And then we also calculate what we call effect size statistics to estimate how important a particular result is that we get from a statistical test. So these are I haven't covered all the possible options here, but there are many statistical procedures. Okay, another way of thinking about it is as a statistical design. So there's certain this is a listing of possible statistical designs that you might be able to use for a study. So you might do a study with just descriptive analysis. You might do a study where you're using analysis of variance, which could be a between groups analysis or a repeated measures design. And then there's correlation, there's discriminant analysis, which is a method of data reduction. There's factor analysis, which is also a measure of data reduction. So and then there's logistic regression. So there's many. These are more procedures, more designs, more statistical designs. You might be using a study using multiple regression. You might be using a study using MANOVA. You could be doing panel analysis. So these are all different statistical designs that you could use for a study. Some of them are more simpler than others in terms of how they would be applied and the kind of measurement that you would need to get to run them. But it's just to give you an idea of the scope of sort of designs available to the person who's doing a quantitative study. Okay, so the most basic type of statistic is descriptive statistics, and we use these to describe a measure, and we also use them to describe the sample in a study. So whether you're doing a sort of scientific-based study or a social science study, we use things like frequencies to describe the measurements and to explain what the sample looks like. Within descriptive statistics, we have what they call measures of frequency, and those could be counts percentages, or a frequency, which is also it's a form of a count. And then we also have measures of central tendency, which are mean, median, and mode. And then we have measures of dispersion, which are range, variance, standard deviation. Those are some of the measures of dispersion. So that's the amount of variation there's around a mean. And then we also have measures of position, which are, we might say, percentile ranks or quartile ranks. So these are some of the kinds of descriptive statistics that we can use for a study. Okay, excuse me. Okay, so when just the figure, so when we're using descriptive statistics, we get counts. We'll look at some examples of counts in a minute, but we also get measures of central tendency, which is the sort of behavior of data around. So we can measure a mean or a central point in the distribution of data points. And there's three types of this figure. Kind of shows a typical normal distribution with an average in the middle, and then that's the middle. This is a perfect normal curve, so the mean will be in the middle of the distribution. And I'll explain how the mean, median, and mode are calculated in a minute. And then we also have measures. The measures of dispersion are how much variation there is around that mean, around the central point of the data. So and we'll look at how those values give us an indication of whether there's a skewness in the distribution, or whether there's or what the curve looks like in terms of the shape of the curve when we have a distribution. And that's important in terms of understanding the distribution of the data, because not all data is normally distributed. And if it's not normally distributed, then we need to understand what the distribution looks like, because that might affect the kinds of statistical analysis that we can do for the data, for the variable. Okay, so there's three measures of central tendency. The first is the mode, and that's the value which occurs the most frequently. So, for example, you might say for descriptive data, the highest frequency category is never. If you've got a never, rarely, sometimes, always scale. The mode is the data response that occurs the most frequently. The median is the middle value in a distribution. So if you have 10 values, and if you rank those values from 1 to 10 in terms of the size of the value, the median will be the middle value. So if you have if you have 10 values, there isn't a middle point. There isn't one data point that's going to be in the middle. You'd need to take the two middle points and divide by 2 to get the median. If you've got 11 values, the middle value would be value number 6. So in the ranking, so that's the median is the middle value. So 50% of the cases will occur below the median, and 50% of the cases will occur above the median. And then the mean is the numeric average. So what we do with the mean is we just basically sum the values that we've measured, and then we divide by the number of cases that we have, and that will give us the average. And then we can also do what we call trimmed means, where we exclude extreme values that influence the mean. So if we have a very high value, which makes the mean much higher, we can remove that extreme value to get a more sort of a trim mean, or a more kind of a mean that's not influenced by this very small or very large value. And then the measure of dispersion is measured using one of the measures for that is the standard deviation, and that's a measurement of how each data point differs from the mean. So what we do is we calculate the mean for the distribution, and then we calculate how different each value is from that mean. And that gives us, there's a formula that we use, which then gives us a standard deviation, which is the amount of variation in the distribution of the data points. We measure this to assess the usefulness of the data. If the values are close to the mean, it means that the data values are more typical of the distribution. if the values are very widely different from the mean, then it means that there's a lot of variation in the data, and that could be a problem in terms of variation plays a role when we're running statistical tests, for example. So the more variation there is, the more difficult it is to sort of look for differences in data in between groups, for example, because the variation plays a role in assessing whether there's whether the groups are similar or different in their scores, for example. Yeah, and then yeah, if the data is from a sample as opposed to from a population, then we use a different measure for standard deviation. But if the sample is larger than 30, then there's not that much difference in the definitions or for standard deviation, and that's an important point in terms of because small samples are a problem statistically. So the idea here would be that if you have a sample size of 30 or more, your measurement of the standard deviation can be considered to be equivalent to a population standard deviation. So that's an important criteria for determining sample size, the bare minimum sample size that you might need for a statistical test. Okay. I'm not going to go through these formulas, but obviously to calculate the mean and the median, we use formulas, and that often scares people off, but they're not actually that complicated. And they nowadays, because the computer can calculate the information for you, we don't need to use the formulas directly. The computer does the full calculations for us. But which is it's useful, but it's also a bad thing in a way, because it means that we don't always understand where the number comes from, and that can be a bit of a problem for understanding the statistics in terms of their meaning. So but just the formula for a mean is just to add the values that you've measured and divide by the number of cases. That gives us the mean. Standard deviations, if you look at the formula, it's the deviation, the variance is calculated by estimating the difference between the mean and the value, each value, and squaring those differences. We need to square the differences to make sure that because your mean is calculated from each value in the distribution, if you were to just simply subtract the mean from each value, you would end up getting a value of a difference of 0 if you total up those differences. So we need to square the data to make sure that we get some measurement of the difference between the mean and the values. And then the standard deviation is the square root of the variance. It's a formula which takes into account it's a form of square root of the estimation of variance. So it's kind of converting the measurement back to what the mean was measured in, or what the variable was measured in, because the variance is a squared value. The standard deviation is the square root of that variance calculation. Okay, so so then when we do dispersion, when we use the summary statistics like the mean and the standard deviation, it doesn't always apply to all variables. It mainly applies to interval or ratio data. So when if you measure something like age in a raw number, for example, or a person's income, we would use the mean and the standard deviation and the median to measure those variables. We wouldn't use a mean to measure a nominal variable like gender, for example, because that's not you don't get an average gender. And there is a question about ordinal data. Technically, we wouldn't take a mean of ordinal data, because ordinal data is a form of it's a sort of scale variable, but it's not a true interval number. But we actually do sometimes, you can use, so some people do treat ordinal variables as being a form of an interval variable. So it's not, some people would criticize that and say it's not appropriate, but it is done. So you'd have to sort of get an idea of what people in the discipline are, what researchers in the discipline are doing in relation to ordinal data. It's because that scale sits in the middle of a true interval data point and a nominal data point. So we sometimes treat ordinal variables as being nominal variables for statistical tests, and then but there are instances where we treat ordinal data as being like an interval variable, just to try and so like in a factor analysis, for example, we do correlations of ordinal variables to assess whether they would be appropriate to be included in a factor analysis. So there are always exceptions to strict rules about how we treat data. Okay, then if you want to get measurements of the difference between values, one option is to use the range. So that's the difference between the highest and the lowest data values. So that gives us an idea of what the range of, say, age is, for example, or you could use that for income or any interval-based measurement. And then the interquartile range is we use that for data which might not have a normal distribution, and that's where we divide the range of data points into 4 quartiles, and then what we're doing there essentially, and then we look at the range between the 25th percentile and the 75th percentile. So what we're doing there is we're cutting out the extreme values, which sit in the quartile between the lowest value and the 25th percentile, and the data that sits in the 75th percentile to the highest value. So those data points will be extreme values, and we cut those out. When we use the interquartile range, we cut those data points out. So it's removing the extreme values from the analysis, or not. We're not removing it from the analysis, but we're estimating what the distribution looks like based on those extreme values being excluded from the distribution. So we can do that with the trim means as well. So it's similar to the trim means, where you're removing these very extreme values from the distribution to make an assessment based without these very, very high values or very, very low values. So so the data is less skewed by removing the extreme values. Okay, I think I've already mentioned this. So not all descriptive statistics are used for all types of measures. So for example, we don't calculate a mean for nominal categorical variables. So we don't have an average marital status, for example. And if we reporting a mode, if we're reporting for a summary statistic for a nominal variable, we would use the mode, which is the highest valued response category. And you can get more than one response category with the same number of cases, which has the highest. So you can get multiple modes for categorical variables. What I was thinking about, and students do sometimes report means for nominal variables. We do see it in when we're looking at sometimes if we ask to look at students' work where they've written up their findings, they will sometimes run means of variables where it's not appropriate, and then we have to obviously try and correct that. So, but it's not something that you just don't do that, kind of thing. Yeah. Okay. So how do we get summary statistics? I'm going to switch to a demo now of SPSS. I just need to get my just check what I need to do here. Okay. So we're going to I'm going to load a data set now, which is looking at student performance on an engineering course at a Technicon. And the dependent variable is academic performance. And I'm not going to do inferential statistics yet, but the dependent variable is going to be academic performance. And the independent variables are did maths, did having exposure to pure maths and physics at school, does that influence their performance on the engineering course? And did does the grade that they had when they entered the program influence their performance on the program? So they could have come in from grade 10 or grade 11 or 12. So that and it's a technicon, so they could come in at a low grade. So the questions that we're asking are, for this study, we'll be asking, do these variables affect the academic performance? But at this stage, we're only interested in the descriptive analysis. We're not going to do the inferential statistics yet. We'll do that a bit later. Okay, so I'm just going to stop sharing the screen and I'm going to start sharing. Where am I here? Okay, so share here. Okay, so you should see on the screen now a data set which has 4 variables in it. Can you see that data set?
Yes, we can.
Okay, good. Okay, so I'm going to run some frequencies just to show you how I'm going to run some frequencies and some summary statistics for depending on the type of variable, just to show you how it's done in SPSS. So the data has obviously been prepared. We've got, I can't remember how many cases. There's 139 cases in the file. Excuse me. So these will be learners. So they'll be students. And then we've got a variable, which is whether the student has had access to physics or maths before they came onto the program. The response options there are yes or no. Then we've got the grade that they entered the program in. It could have been grade 10 or grade 11 or 12. And then this is the academic performance. The academic performance is rated from, I think, 0 to 12. So where 0 would be a poor performance and 12 would be a strong performance. Okay, so to run statistics in SPSS, we go to the Analyze menu. So this is the Analyze menu, and you'll see there's a whole range of statistical procedures on the menu here. There's descriptive stats. I'm going to skip Bayesian statistics for now. Tables, compare means, mixed models, correlate, regression, classify, dimension reduction. Remember, I said there's a range of dimension reduction statistical procedures that we can use. There's scale. This is where we measure reliability. I won't talk about I'm not actually going to talk about multiple response, but that's more of a descriptive analysis. Yeah. So these are but most of the tests, all the tests that are available in SPSS will be under this menu. So if you look at the menu here, where do you think we would find, where would we run a frequency? Okay, I'm giving you the hint here. Okay, there's an option here which says descriptive statistics. We know that frequency is a descriptive procedure, so we're going to go descriptive statistics frequencies. Okay, just to say, there are a couple of other menus here. Sorry, another menu options where you can do descriptives or explore. We sometimes use those menu options as well. So they explore, for example, you can get the same kind of information that you can get from the frequency procedure, but it packages it in a different way, and it might have some extra. It does have some extra statistics which you wouldn't get from the frequency menu. So so you might need to kind of I think there's different options on these different menus, but I mainly use frequency or explore. I don't think I ever use the descriptive menu because I can get most of the information from the frequencies or the explore menus. Okay, and we'll come back to crosstabs a bit later. Okay, so I'm going to run frequency. When we run the frequency menu, you should see a option on the screen now saying frequencies. There's a box saying frequencies. Can you see that screen?
Yes, we can.
Okay, so now I'm going to treat the 2 types of variables separately. So the first variable I'm going to put in here are the categorical variables, which is the question about learning pure maths and physical science before coming to the technicon, and then the grade that the student had completed when they entered. So the reason why I'm treating them separately is that I'm going to be using, I don't need a mean and a standard deviation for these 2 categorical variables. So I'm going to run them separately just to show how we treat the different kinds of variables. You'll see that this is interesting. This has got the wrong formatting, but let's not worry about that now. Okay, so the statistics, under this, there's a menu here that says statistics. So when I open that, it comes up with a range of summary statistics that I could use for for these variables. But because they're categorical variables, I'm not going to use mean, median. I might use mode. That's the kind of really the only reasonable central tendency variable that I might use here. So that's, I'm only going to choose that one here. I'm not going to worry about skewness, kurtosis, and so on for these variables. I'll do those for the other variables. Okay, so, and then you can draw a chart with SPSS. I'm going to run a bar chart. If you're doing a categorical variable, you wouldn't use a histogram. So that's the wrong kind of chart to use for a categorical variable. You would use a pie chart or a bar chart for a categorical variable. And then you can choose to display the chart with frequencies or percentages. Percentages is usually more appropriate. But so I'm going to run the chart now, but I wouldn't normally run a graph for a two-category variable. That just to say that I don't think it's a very useful kind of display. But I'm just going to do it to demonstrate that we can do it. Okay. Under the menu, there's also a formatting menu where you can change the appearance of the tables. So you can change the way the counts are, or the way the tables, the way the variable is displayed in the table. So I'm using ascending values, which will keep and that's based on the coding of the variable. So if no is coded 0 and yes is coded 1, it's going to display the table in that order. But you can change it so that you do it based on the count. So it's not based on the response that you've given the variable. You can do it based on which response has the highest frequency. And sometimes it's useful to do that. In this case, I'm not going to worry about that. Okay. You can also suppress tables with many categories. It's not normally you don't normally need to do that. There is another option here, which is also I don't use it for the output that I generate, but you can create APA-style tables, and I'm just going to leave that off for now. And then the style and the I don't play around with the style, and bootstrapping, we're not going to do that now because it's not relevant for the sample. Okay, so I'm going to click OK to show what we get for the output, and now I'm going to have to toggle the screen because the output file comes up in a different window. Okay, so I'm going to share this screen. So you should now see an output window which has got some tables in it. Can you see that?
Yes, we can.
All right, so this is the frequencies that we get for the two variables. These are the two categorical variables. So we've got for the question, and just so I mean the computers process that really quickly. Obviously, it's generated the output for 139 cases in literally less than a second. So that's the one advantage of using a computer-based program for running statistical analysis. So what this table tells us is that we've got 44 students who didn't have pure maths or physical sciences before they came onto the program, and 95 did. And I'm going to ignore this percentage column, and I'm going to ignore this cumulative percentage column because they're not relevant for this particular output. But I'm going to show you what happens if we use the APA style output. So 31.7% of the sample said no, and 68.3% of the sample said yes. So that kind of tells you that most of your students, almost 2/3, well, just over 2/3 of your students had access to or had exposure to maths or physical sciences before they came onto the program. And because this is linked to engineering, so it's an engineering program, the idea here would be to say is how important is that exposure to the student performing well on the program. We're going to come to that relationship later. But the reason why we're measuring this is that the literature probably would say that having exposure to pure maths and physical science is an advantage if you're coming into the engineering field. And I think that's a fairly well established kind of link between those things, between the subjects and the field. All right, and then the second variable is which grade the person came into. So the person was in grade 10 or in grade 11 or 12. So almost 80% of the sample were in grade 11 or 12 when they came onto the program, and the other 20%, just over 20%, were in grade 10. And again, the idea here would be maybe people coming in from grade 10, excuse me, or maybe the students coming in from grade 11 or 12 would be more advantageous than the students coming in at grade 10 because of their more extensive exposure to learning at school. So that's the idea behind measuring that variable. And there might be something in the literature which says, the longer the learner has been at school, the better they adapt to the program. So that would be the idea behind that, measuring that variable. These are the graphs. I don't normally use SPSS graphs. I normally convert the data into Excel and draw the graph in Excel because it's partly because it's easier to, I think Excel graphs look a bit better, and I think it's easier to work with graphs in Excel than it is in SPSS. So this is just to show you that you can generate a graph from in SPSS. I don't often do that, but you can do it. Okay, so, and it's also to point out that the type of graph should be the kind of graph that you use, the type of graph that you use must be appropriate for the kind of variable that you're measuring. Okay, so, and I'll talk about reporting this when we get to that slide. It's just shortly. Okay, so are there any questions about this output at this point? Is it all sort of fairly straightforward? Do you have any questions about that? Okay, is everybody okay with that? Okay, so I'm just going to run I'm going to try and do this without, or maybe I'm just going to rerun this analysis using the option of checking the create APA, and I'm going to take off the chart because we don't want it to come out again. So I'm just going to rerun this. Can you see there's a new output now with a much simpler table?
Yes, we can.
Yeah. Okay, so if you check that use APA style, it gives a very abbreviated version of this table. So we've got a more complicated table here, which has a percentage and valid percent. So what this APA style will have done is it's taken it will have taken this valid percentage and the frequency. So it's just extracted the frequency and the valid percent and presented those in a table. So it's cutting out this percentage. I'll explain the difference between these, and then the cumulative percentage, which is not really needed for it's not the kind of percentage we would use for a categorical variable. So this is a much more abbreviated and sort of more appropriate form of the table for that particular thing, but the problem is you need to format it in such a way. So it's a bit messy with the code here, but that's fine. Okay, so you can produce more simple tables, which are more appropriate for the type of variable that you're measuring. Okay, I'm just going to stop sharing this because I need to go back to the data window. Okay, so then if you want to, that's your categorical variables. Those are quite straightforward to measure. Then if you want to do a variable, this is a numeric, it's not actually classified as a numeric variable here, but I'm going to treat it as a numeric variable in the analysis because it is a number. It is a score of 0 to 12. So this is the academic performance, and we'd want to get different kinds of statistics for this variable. So we'd want to get, say, a mean, a median, Some wouldn't be relevant here. If you were measuring something like income, for example, you could get the total income for the entire sample by using the sum, but you don't necessarily want to get the sort of total marks that the class has got, unless you wanted to compare that class to another class, for example. I'm also going to measure skewness and kurtosis here, just to show you what they measure. And then I'm also going to measure standard deviation. So you could also you can also measure minimum maximum.
Sorry, Dr. Devi, we can't currently see the screen.
Okay, what are you seeing?
We can just see the tiles of all of the participants.
Okay, let me try and share again then.
Thank you.
Thanks. Yeah, okay. It's not. Okay, let's try again. I think it's jumping between the screens. So can you see the data set now?
Yes, we can.
Okay, so yeah, I'm going back to the menu to run the frequency for the interval variable, which is the academic performance. So this variable is scored from 0 to 12. So I don't want this APA statistics table because I want to show you how the cumulative percentage works. So under statistics, I'm going to choose mean, median. I can keep the mode as well. Can you see this window now? It says frequency statistics, and there's,
yes, we can.
Yeah, sum. Okay, we're not going to take the sum. We don't need the sum of all the marks that the students obtained. I'm going to measure skewness and kurtosis just to explain those. And then we've got standard deviation. You can measure the minimum, maximum. It's sometimes useful to report the minimum score and the maximum score. And then you could also measure variance, range, and standard error of mean, but I'm not going to use those now, just to, and this is where you would measure your percentile. So if you wanted to group the scores into, say, groups of 4 and into 25 percentiles, or 20%, excuse me, 20% groups, which would say quartiles or quintiles, or even deciles, which would be 10 groups of marks. You could do that under percentiles. Yeah, I'm not going to do that now because we don't need to use that, but that's it. Okay, so I've chosen. You can choose what statistics you want here. I'm just choosing some of them. And then under charts, the appropriate chart for a range of marks would be a histogram. And then SPSS also allows you to show a normal curve on the histogram. So I'm going to do that just to make the point about the skewness. And that's then I'm going to continue from there. Okay, so and this is probably the graphs. If I was drawing a bar chart or some kind of bar chart, I would probably convert the data into Excel. But for a histogram, I would use the SPSS graph there, because it's not that easy to take the data into Excel, and I'm not going to change anything here into Excel and then run the histogram. So for histograms, I would tend to use the SPSS graph. Okay, so I'm just going to click OK here, and then we just need to toggle again. Okay, so I'm going, where am I now? I've lost this. Stop sharing that. Okay, I'm just toggling to the output window now. So SPSS creates these separate windows. So the data, it creates a separate file for the output. So this is it's a file with a different structure. That's why I'm having to toggle between the different windows. So you can save this file, but you can only read this file I'll just talk about the saving of the output files. I can save this output file, and then but you can only read this file using SPSS. So it's not, so obviously I always save the output file, but I can only read it with SPSS. So what I do was, if some of the students that we support won't have SPSS, so what I do is I export the file. I'm just going to save this quickly. I'm just going to save it. I'm just going to say temp here. Okay, and then it's not working. I've already got a temp. So make it temp1. Okay, so we can export the file. So you can export to different formats. You can export, I normally export to Excel. And then you can also export to Word, for example, though. But there's certain things you can edit once you've exported. So, for example, you can do things with the tables, but you can't edit the SPSS graph in Excel, for example, or Word. You can only edit the graph in SPSS. So there's limitations to the exporting. Allows you to convert the information into other formats, but there might be restrictions on what you can do with that information once it's in the format. The tables are fine. You can cut and paste and do things with the tables, but the graphs, for example, you can't edit an SPSS graph when it's been moved into another program. You can only edit that graph in SPSS. So just be aware of those kinds. I'm not going to do this export. So that's, yeah, I just wanted to show you that you can do it. So you can, so SPSS saves this output file as its own format of file, which can only be read in SPSS, but you can export the file to another format, Excel or Word, for example. All right, so this is the result for the, sorry, can you see on the screen now a table saying statistics and academic performance with one?
Yes, we can.
No, yeah. Okay. So this variable here, the average score, the score ranges from 2 to 12. The minimum score was 2, so at least one student got a score of 2 for their performance, and then the maximum was 12. I don't know if the maximum was 12 or 15 or something like that, but it's probably that the 100% would be 12, a mark of 12. Okay, so we also get the mean value is 9.3, which is quite high if the maximum is 12. The median is 10, which is also quite high, and the mode is 12. So the highest frequency was 12, which was the best mark. So when the mean, median, and mode are equal or similar in value, then that suggests that we have a normal distribution. But you can see we've got the mean is lower than the mode, quite a bit lower than the mode, which suggests that we're going to have a skewed distribution. And if we look at the skewness, it's not a high level of skewness, but that's partly because we don't have a wide range of values. But it's a negative skewness, minus 7.70. So I'll show when we look at the graph, I'll explain that. So we've got, and then the standard deviation is 2.7, which is not, that value doesn't really have a, it's difficult to interpret that value, except to say that because there's no right or wrong value for the standard deviation. The bigger the value, the more variation there is in the data, basically. So for a range of 1 to 12, a standard deviation of 2.7 is quite high. So it does look like there's quite a wide distribution within the data, and we'll see that in the frequency table below. Kurtosis refers to the shape of the curve, so we'll look at that when we look at the graph as well. And then I'm not going to worry about the standard error or the minimum, yeah, and then the minimum maximum are fairly straightforward. Okay, sorry, can you see my cursor on your screen, or can you just see the tables?
We can see the cursor.
Okay, good. Okay, so this is the distribution of marks. 2 students got 2, 2 students got 3, 7 students got 4, 5 students got, 3 students got 5, 14 got 6, 11 got 7, 54 got 12. Okay, so that's a good, there's a sort of 40%, just under 40% of the sample got sort of top marks for their performance. This is why the mean is sitting a bit lower, because there's quite a few students around 9, 10, and there's also quite a few students further down the performance range as well. So the difference between this percent and valid percent, I can't demonstrate it here because there's no missing data. But if you have missing data in your distribution, the valid percent will only calculate the percentage for the cases which are there. I'm going to be using another data set later on. So this one doesn't have any missing data, so I can't demonstrate it here. But if there was missing data, this percentage here would include that missing data in the frequency, and then the valid percent would only take into account the cases where there is a response for the question. So you get a difference in the numbers if there was missing data, but there's no missing data here. Okay, the cumulative percentage is just adding up the percentages. So 1.4 plus 1.4 will give you 2.9. It's obviously rounding off, so it's not. It should be 2.8, but there'll be more. It's only using one decimal here. So if you added another decimal, it would probably round up to 2.9. If we add 5, that goes to 7.9. If we add 2.2, that goes to 10.1. If we add 10.1, that goes to 20.1, and so on. So this cumulative percentage is useful because it tells you sort of, for example, that 20% of the sample got 6 or lower for their performance. And then just under 60% got 10 or lower. So it's useful. This is because the distribution is quite clustered around these higher values. It's not giving nice clean breaks for, it's not showing us a 40% break or a 60% break, although it's quite close there. So you'd say 20 is 6, just over 40 is 9, just under 60 is 10, and then and then we've got this, or in fact it's around about 10 or 11 because there's this big chunk of just about 40% of the sample sitting on 12. So that's the table here. And then we wouldn't normally report a table like this because there's a lot of detail in it. We'd normally report the summary statistics and maybe the minimum maximum. And you might group these into groups rather than based on the cumulative percentage or some kind of decile or quintile grouping. This is the graph. So you can see it's quite a skewed distribution towards it's got a negative skew, which means the tail of the distribution moves off to the left of the distribution. So we've got because we've got these few students who are doing poorly in terms of their performance, and we've got lots of students doing well. In terms of and then also, so that's the skewness is negative, so it's moving. The tail is off to the left of the central distribution, which is around about 10, 9 or 10. And then the kurtosis refers to the shape of the curve. So a normal distribution would have a curve which peaks and then drops down. This curve is much flatter, so that will be reflected in the kurtosis value, which is minus 4.92. Okay, so if you had a normal distribution, that kurtosis value would be different. Would be very different to a minus 0.4. It would be closer to 0, for example. So that distribution, this is not a kind of very clearly not a usual normal distribution. It's a skewed distribution with a very sort of flat kurtosis. Okay, so and then that kind of distribution that you have will determine whether what kind of statistics that you can do. So you'll see when we do the parametric tests, one of the assumptions is that the dependent variable has a normal distribution. And in this case, our dependent variable doesn't have a normal distribution, but we have a big sample. So that will allow us to it allows us to proceed with a test even though we don't meet the assumptions for the normal distribution. We could also try and adjust this variable, to make it more normal. But I would be concerned about this very large group in this higher category, because even if you convert the data or we call it transforming the data, those data points are just going to move to a different place. So they're still going to sort of dominate the distribution in a problematic way. Okay, so those are your basic stats. So the question then is, how do you write up those statistics? I think that's the next question. Is then how do you? We're going to look at the relationship between the variables a bit later, but then the question would be: sorry, can you see my presentation now?
Yes, we can.
Okay, but it's not moving. Okay, there we go. It's just moving now. Okay, so the question is then, how do you write up the findings from the descriptive analysis? So there's different ways that you could present those results. So if you had when you've got two variable, sorry, a variable with two categories and there's percentages for each one, I would probably just present that in a narrative, as in a paragraph, in a written form, to say that this number and percentage of the students were had exposure to physics and maths, and this percentage didn't. You could use a graph, but as I mentioned, I don't think a graph is very useful for two categories. It doesn't. You can just say that you can give the result much more simply using a narrative, just using a short sentence or two. So you don't need to. To me, it's not necessary to use that kind of display. It's like filling up space when you don't really need to. The mark result or the performance result is more complicated because there's more information to present there. And again, you could kind of present it in a narrative way of saying the average performance was such and such, the median was such and such, and there was the minimum, maximum, and then there was a negative skewness to the distribution. Or you could maybe present it in a graph format. That's a bit more interesting in a graph format. As a histogram with maybe a normal plot on it. But there is and I think I've mentioned that the point about using it's good to use graphs if they're making the point. Visually, they're quite impactful because they're providing a visual image of the distribution. But you also have to weigh up the space that they take up, and do you need that sort of graphic? So I tend to prefer tables rather than graphs because I can see the numbers in the tables, but that's just my personal preference. Other people might like doing graphs. So this is just some examples of tables. We can also generate custom tables using SPSS. So these are just some examples of those. But when SPSS generates the tables, they generate a table, one table with the percentages and frequencies. So this is a set of questions measuring students' likelihood of returning to the program if they pass their modules or if they fail their modules. And it's measuring the likelihood of them returning. And there's a number and a percentage. I'm not going to go into detail about the results, but this table shows you the count and the percentage, and the table has the mean and the standard deviation. So it's difficult to get them into the same table, which you would want to use for presentation. So the point about this is that you sometimes have to edit the information to get it into the format that you need. So then this is from a resource. There's a book called by Morgan et al. Called From Numbers to Words, which is a nice resource to use for working out how to present your findings. So they have a table. This is their example of a table, which is a similar table to the one. It's got similar information to what I was showing in the previous slide. The difference here is that they've combined the mean and the standard deviation into the table. And remember, I was saying we wouldn't normally use the mean and the standard deviation for an ordinal variable, but it is a useful way of summarizing the distribution. So we do it. So people do it. Although the purist would say you shouldn't be doing that, but it still provides a useful way of summarizing the distribution. What I don't like what they've done here in this table is what they've done is in the original instrument they would have measured strongly agree, neither agree nor disagree, disagree, and then strongly agree. So they had 5 categories, and you can see they've got 5 categories from the mean, which is 3.86, 3.6. So that would be the average out of 5, from 1 to 5. But what they've done in the table is they've lumped they've kind of grouped the percentage of strongly agree together. So it's 75%. And it's not, I think I would have kept those separate and not grouped them together. into those categories, because the mean is not reflecting the distribution in these 3 categories. It's measuring 5 categories, not 3 categories. Yeah, and then the other point to make from this is that if we look at the previous table, in this table you've got the count and the percentage, but you don't necessarily need both of those, both numbers. It's nice to have them both, because then you've got more information. But if you look at the table here, they've just provided the percentage, and then they've got the number of cases. So you can, if you want to know what the count is, you can say 75 times 128 gives you whatever the number is, and that will be how many of the participants chose strongly agree and agree. So it's the point about that is it's about being you need to present the statistics, but you don't want to you want to kind of simplify the presentation, but also to the extent where the person can work out what's going on. So I can work out from this table how many people would have said strongly agree without seeing the actual number that agreed or disagreed. But you could also put the number into the table as well. It would just make it a more complicated and bigger table. So this is a very simplified, a very sort of it's a very kind of succinct way of presenting information. This is from a book, as I said, called by Morgan et al. Called From Numbers to Words, which there's different editions of that. I think there's the most recent one is about 2017, and it's a very good book for using so it gives advice on how to present statistical information. Okay, and this is the resource. So it's Morgan, Reichart, and Harrison. I think the most recent edition that I've seen is 2017. And the book is called From Numbers to Words, Reporting on Statistical Results for the Social Sciences. So that, and again, although it says for social sciences, it's not, if you're working in science and using the statistical procedures that they are covering in the book, the same, it would apply whether you're a scientist or a social scientist. So it's not, I think the issue is that they might not be covering some procedures that would be used in science. But in general, if you're using the procedures, then they would apply whether you're in social science or science. Okay, so that's a good resource for if your students are doing statistical work, or if you're doing statistical work, it's a good resource to look at for relevance for your for the statistical test that you're using. The other thing this book has is they have a summary table, which is another useful resource in this book, is a summary table of what statistics, when you run statistical tests, you'll see later, you get a lot of output, and you don't need to use all of it for reporting. So and their book summarizes. They've got a summary table which advises what particular statistics you need to report when you're reporting on a particular statistical procedure, which is very helpful. Okay, then I'm just going to start this topic, and then we can have a break before we move on to I'm going to go through some sort of theory. And then we can have a break after that, because I know you'll want to break. Yes, sorry, there's a hand up. Yes, yeah.
Hi, good morning.
Yes,
I have a question about reporting means and medians in terms of normal and not normally distributed. So when the data is not normally distributed, I tend to report median, but it seems like I'm being a little bit pedantic about it. And if you have a big enough sample, that's not necessary. You can go with the mean and the standard deviation.
No, so it's very no. So if you don't, I think it's more about whether you apply the test or not. So if you've got a skewed distribution, you should report the median and the mean, and then So I think I wouldn't just report the mean. I would report the median, because you need to show that the distribution is skewed. I think the question with the issue with the sample size is around is around whether you can so when we come to use certain tests, there's assumptions behind using those tests, which I'll get to that shortly. And that when you that's where the question of how critical is it that you have distribution issues with your data, and can you sort of put those to one side and proceed with a parametric test as opposed to a non-parametric test? So I think I'm not saying that you shouldn't report the median or use, say, an interquartile range instead of a standard deviation. So if you have problems with your distribution, or if your distribution is not normal, the suggestion would be that you use the median and an interquartile range rather to describe the distribution, because then that's taking out the it's taking out those extreme values, or it's accommodating for those extreme values. So I'm not saying that you shouldn't do that. I'm just saying that when it comes to using statistics, you might be able to overcome some of the assumptions that you're not meeting if you have a decent sample size. So yeah, definitely, if you've got skewness issues, you must definitely report the median. So yeah, I'm not saying you shouldn't report it. Okay.
But you would suggest that both is reported. Is that what you're saying?
Yes, yeah, because that then shows if you report both of them, then the reader can see that there's a sort of huge gap between them, and that then demonstrates that that shows that, because if you just show the median, unless you write somewhere that you're going to report the medians because there's a high amount of skewness in the data or whatever, then you might not need to. But I think the more information you present, the better indication the reader could get of the distribution issues. Yeah.
Okay, thank you.
Okay. All right. So descriptive statistics are very useful, but they don't give us any indication of the relationship between variables. So they have limits in terms of their usefulness in terms of moving beyond the simple description of a variable. So we then move on to inferential statistics, which we use to test associations, correlations, relationships. We use inferential statistics to test hypotheses and theory, and we use inferential statistics to infer about population from the sample that we've obtained. So these are some of the sort of purposes of using inferential statistics. So just some theory. I'm not going to go into a lot of detail about statistical theory, but just to try and give you an idea about what the theory is behind statistics or behind inferential statistics. So there's a very famous research philosopher called Popper, who made the argument that theories can't be verified absolutely and forever. So we can't ever say that anything is always going to be true, but we can falsify a theory. So we can try and prove that a theory is wrong to a certain level of certainty. So that's the idea behind statistical testing, is that we can't ever prove anything to be true absolutely, but we can, with some data, show something. We can prove something to be incorrect to a certain amount of certainty, to a certain degree of certainty or probability, and that's from a famous text, The Logic of Scientific Discovery. Okay, so we're going back to this idea of which we started out with about a theoretical proposition. So we're looking at these two variables. That's a very simple design: construct X and construct Y, and then we want to try and see if there's some kind of relationship between those variables. So that's the kind of general idea behind inferential statistics. So we're going to look at the link between two variables, and I'm using the word link because I don't want to use the word correlation or association, because that has those have specific meanings in statistics. Okay, so the way a statistical test would work, or a hypothesis test, is we state a null and alternative hypothesis. So we've got these. We might have a very simple hypothesis about two variables, and I'm not giving a specific example now because the way we will frame the hypothesis will depend on the kind of measurements or the kind of variables that we're working with. So we'd start by stating the null and alternative hypothesis, and we'll have examples of those later. Then we decide on an alpha value, and it's a hypothetical value that we decide on, and I'll explain how we do that a bit later. Then we choose and calculate a statistic. So that's going to be based on the kinds of variables that we're measuring and the kind of relationship that we want to test. So as I've mentioned, there's many different kinds of statistics. Then we calculate the degrees of freedom and estimate a p-value. And then we compare the p-value to the alpha value to decide on the hypothesis. That will just determine whether we reject or accept the null hypothesis. So that's the kind of basic process in hypothesis testing. There's a few steps involved. It's always done pretty much the same way. We follow the same procedure. So whichever test we're using, we'll follow the kind of the hypothesis might change, but the procedure of choosing alpha values, choosing the statistic, calculating degrees of freedom and estimating the p-value, and comparing p to alpha follows the same kind of process. Okay, so statistical theory is underpinned by probability theory, and parametric tests are based on the theory of normal distribution. So I'm not going to go into detail about a lot, but this is an example of a normal curve. So when we measure things in nature or in society, many variables take on a normal distribution. So, for example, if you were to take a population of people and you were to measure their height, you'll find the majority of people have an average height, and then there's a much smaller number of people who are extremely tall and a much smaller number of people who are extremely short. So that's the idea behind the sort of normal pattern, is that most people will sit in a sort of middle distribution, and then there will be a few outliers who are either very tall or very short. And the same thing would happen with weight. Most people are sort of average weight, and then there's a few people who are very, very low weight, and then a few people who are very extremely high weight. So that theory, when we have a normal distribution, we can estimate how many cases or how many people or how many objects that we're measuring will fall within certain standard deviation of the distribution when we have this normal curve. So you've got your middle value, and then we've got one standard deviation away from the middle value, which is the two lines, the two sort of upright lines on the left and right of the middle value. So those, we can estimate how much of the sample will fall within those two standard deviation points. And then the same thing for the next level of standard deviation and the third level of standard deviation. So, for example, when we have the normal distribution, we know that roughly 68% of the sample will fall within one standard deviation away from the mean, and then another 28% will fall within the second standard deviation. Then about 4% or so will fall within the third standard deviation away from the mean. So because we've got this very nice structure, it allows us to make estimates about the distribution of the sample. So that's or the distribution of the measure. So that's one of the principles underlying statistical theory for parametric testing, but it doesn't work for non-parametric testing. So the normal distribution allows us to estimate values within given probability levels, and it also allows us to estimate confidence intervals. So what are our confidence intervals around a mean? And then when we're using statistics, we want to infer about the population, but we only have the sample from the population. We don't have the measurement for the entire population. So we use the standard error, which is the standard deviation of sample means, as an estimate of the population mean. So that's what we use this statistic, which is based on the sample, to estimate what the population mean might be. So that's an important statistic, and I'll explain how that changes. I just want to go back to this diagram here. Many variables don't have a normal distribution. So, for example, that performance variable that we looked at just now doesn't have a normal distribution. But if we take the issue with sample size is that if we had a big enough sample, and if we took subsamples from that sample and then measured the variable for those subsamples, those subsamples could take on a normal distribution. And that's why, so there's something called the central limit theorem, which is when we have a big sample, we can assume normality even if the variable doesn't have normality, because if we took subsamples from that variable, from that sample, we would achieve a normal distribution. And that's one of the reasons why when we have a large sample, we can assume that we have a normally distributed variable, even though it might not be showing up as having a normal distribution when you take the entire sample measurement. Okay, so and there's actually a nice, I think it's actually in the Kirkwood and Stern book on medical statistics, where they have a nice example of how that works to get where if you have a big enough sample and you take samples from that sample, those samples will have a normal distribution. Okay, so this is also relating to that. So what we're trying to do is we end up with a sample which is the kind of curve at the bottom of the distribution here of the four images. So that's the sample that we take, and that might differ from what the population looks like. But we need to estimate about that population. So it's kind of trying to obtain part of doing quantitative research is trying to obtain a sample which has sufficient representation of that population, not to be too far away from it. Otherwise, we're going to have otherwise we're not going to be representing that population very well. So standard error, that measurement of standard error, which we're using based on the population, it's based on the sample, but we want to use it to estimate the population, is influenced by a number of factors. So and remember I mentioned about variation or deviation earlier, saying that if we have a higher standard deviation, it's not a good thing. So if the standard deviation of the sample is high, then the standard error will be high. So which means that we've got a sort of a value and we want our standard error to be low for estimating. So if we've got a sample with a lot of variation in it, it's not going to estimate the population very well. And then if the sample size is large, the standard error will be smaller. So the bigger the sample, the lower the standard error is going to be. And that's why we always try to get larger samples with quantitative studies, because we want to bring down that value of the standard error. And then if the proportion of the population covered by the sample is high, then the standard error will be small as well. So obviously, that's going back to this idea that we're trying to measure this target population. So if we've got a good representation from that population, we're not going to end up down here. We should end up sort of more closer to what the population looks like, and that's going to be better in terms of representation. So the ways we can try and improve the standard error for measurement is to get bigger sample sizes, a more representative sample, and to make sure that not to make sure, but to try and get a lower standard deviation for the variable that we're measuring in the sample. Okay, so that's some of the things we can try and control to get a good representation of the population. Okay, so we start with the hypothesis, and when we have a sort of statistical hypothesis, we have a null hypothesis and an alternative hypothesis. The null hypothesis is stated to reflect a state of independence or no difference or equality. So, for example, we might say ownership status, which is measured as public or private, and quality of transport logistics are independent. So, depending on whether the dependent variable would be quality of transport logistics, and the ownership, that would be our dependent variable, and then the ownership status would be, whether it's private or public, would be the independent variable. So we start off by saying that those two, for those two groups, the quality would be, or those two variables will be independent, or that there is no difference between the proportion of private and public companies reporting different rating on quality. So there we'd sort of say there's no difference in the rating for the two types of group. And then, or we might say something like the average profit made by public and private logistics companies is equal. So we state it as a equal or no difference statement for the null hypothesis. The alternative hypothesis is stated as two variables having some dependence, or there being a significant difference in the ratings, or that there would be a difference in the average profit made by the two types of companies. So the null hypothesis is stated as no difference, equality. The alternative hypothesis is stated as there being a difference, or there being some inequality between the groups. Okay, then we decide on an alpha value. So if we develop a test, we need to make a decision to accept or reject the null hypothesis. And the following scenarios can occur. So we get, in the real world, the null hypothesis could be true or false. And we might conclude from the test that we do that the null hypothesis is true or false. So when in the real world the hypothesis is true and we conclude from the test that it's true, then we've reached the correct result. And if in the real world the null hypothesis is false and we conclude from the test that we do that it's false, then we also would be correct in our decision. If in the real world the null hypothesis is false, and we conclude from the test that it's true, then we make what we call a type 2 error. And if in the real world the null hypothesis is true and we say it's false as a result of our test, we make what we call a type 1 error. So the alpha value that we set for our test, it's a virtual, or it's a made up value. It doesn't have something. It's something that we don't measure it. We make it up. We set it. That level of significance is stated before a statistical test, and it gives us the probability of rejecting the null hypothesis when it's actually true, which is a type 1 error. So traditionally we use alpha values of 0.05, 0.01, or 0.001 because we want to minimize the possibility of rejecting the null hypothesis when it's true. We don't want to say the null hypothesis is false when it's actually true. So we set this alpha value to try and prevent making a type 1 error. The reason for using 0.05 or 0.01 or 0.001 will depend, or the decision about using that value will depend on the severity of impact if you make a mistake. So if you're doing social research where there's not any significant sort of bad outcome if you make a mistake, we would set the value at 0.05, and that's usually the value we use for most of the research that we do. If you're doing medical research where if you're testing a drug, and that if you make a mistake about the drug working, and that could have a severe impact on patients dying, then you use a 0.001 level. It's a much stricter level of confidence that you want to apply to the study. So and under those kinds of circumstances where if you're testing drugs, for example, you really don't want to be making mistakes with with decisions about with statistical decisions. So you set a much more stringent, a much more serious confidence level of having the correct result for your test. Okay, so this is where the alpha value comes from. As I say, for most of the research we do, we work with a 0.05 level. But if you're working in the medical or science fields and your research would have a serious impact, or making a wrong decision with your statistical test would have a serious impact on an outcome, then you need to be using a stricter level of confidence. I was actually reading something where they were suggesting that you could use a 0.1, which we do if you've got a small sample size, but I'm not sure that's such a good suggestion. But anyway, I think it's to do with the idea there being that when you have a small sample, you might be less likely to make a type 1 error. But that's I'm not sure that's I don't think that's necessarily a good suggestion. Okay, then the power of the test is dependent on the size of the sample, and this is a quote from Palant. So according to Stephen, when the sample size is large, for example, 100 more subjects, power is not an issue. But when you have a study where the group, and this is the suggestion about making a less strict alpha value. When you have a study where the group size is small, for example, 20, you need to be aware of the possibility that a non-significant result may be due to insufficient power. So it means that you getting a non-significant test result because your sample size is small. So Stephen suggested when small group sizes are involved, it may be necessary to adjust the alpha level to compensate, so to set a cutoff of 0.1 or 0.15 rather than the traditional 0.05. But I'd be a bit sort of nervous about doing that. Since I've been doing research, we've always worked on a 0.05 level as the weakest confidence level. Okay, and then there are tables available to tell you how large your sample needs to be to achieve sufficient power. So I think I might have shown you that table in the sampling session where they give you, it's a table. There's also online tools available where you indicate what your population size is, and then it gives you an indication of what sample size you would need to reach a confidence level of 95% or 99% or 99.9%. So so that, and obviously the stronger the confidence level, the bigger your sample is going to need to be. Okay. So small samples can make significance testing insensitive. The idea would be to try and get a larger sample size. The other option would be to increase the confidence level, but I think that's a bit of a problem. And then very large samples can make statistical tests overly sensitive. So when you've got a very big sample, even small differences become significant. So that's statistically significant. So the suggestion is that you also calculate an effect size, which is a statistic which over and above the statistical significance tells you whether there's a sort of practical significance to the result. And that does take into account the sample size. So that's an option for sort of trying to deal with large sample sizes always showing up significant results. Okay, I'm nearly done with the session, and then we're going to have a break. So type 2 errors, which are not rejecting the null hypothesis when it's false. So that's where the null hypothesis is false, but you say it's true from the result of your test. Those are often made when there's a sample bias. And one way to try and minimize those kinds of errors is to get a decent sized sample and a representative sample. So these are sort of steps you can take, or your student can take, to minimize the the two types of errors. Okay, the p-value is that's also a statistic that we get, but that's generated when you run the statistics. That is the probability that a difference. So when we run the test, we'll do some later. That's the probability that a difference as large as the obtained difference from the data would have come about if the sort of null hypothesis was true. So the p-value is calculated after the statistical test, and it's termed the observed significance level. So we'll look at the p-value a bit later in a real example. And when the critical thing for making a judgment about the statistical test is if the p-value, p means probability, if the probability value is less than the alpha level, which is the value that we set, then the null hypothesis, then we reject the null hypothesis. So that's how we make the decision about the test, and what that would mean is the difference observed, the difference that we're seeing in the independent or the dependence that we're seeing or the difference that we're seeing in the data can't be due to chance alone. It must be due to some kind of relationship between the variables. Okay. The statistic that we choose will depend on the variables that we're working with, and then because we're using software, the statistics, the software calculates the statistic for you and the p-value, but you have to decide what statistic is most appropriate for your hypothesis, and that will depend on the kinds of variables that you're measuring. So we'll look at some examples. Okay, and then confidence intervals can be calculated when we have a normal distribution, and that allows us to estimate the range within a given percentage of values for 4 or possible means for 4. Okay, and then there are two main groups of statistical tests: parametric and non-parametric. That's other than the other kinds of tests. And then we're going to now start talking about parametric tests. We're going to take a break. So let's take a break now. And then when we come back, we'll start covering parametric tests. Okay, so how long would you like for your break?
Can we have 15 minutes?
Yes, sure. Let's meet at 11. Okay, so let's go to 11. Is that all right? Yeah.
Thank you.
Okay, good. Okay, so we'll start again at 11. Right, we're back again. It's very hot in Joburg today. I hope it's those of you who are in Joburg are in a suitably cool space. Right, what do I have showing here? Right, so I'm going to talk about parametric statistical tests. So this is a particular kind of test which is, we use these tests to test associations and hypotheses and infer about the samples. Some examples of parametric tests are the independent samples t-test, one-way ANOVA, paired samples t-test, the repeated measures ANOVA, Pearson's correlation, and then there's the various forms of regression. We've got linear regression, logistic regression, binomial regression. So there's lots of different types of tests that we can use. There's a much wider range of parametric tests than non-parametric tests. When we use parametric tests, there's certain assumptions for parametric tests. So the first one is that the level of measurement, the test assumes that the dependent variable is measured on an interval or ratio level. So it's using a continuous scale rather than discrete categories. Okay, but there are always exceptions to these assumptions. So for example, when we do a binomial regression, it would be with a categorical outcome variable. So it's not, although there are these assumptions, there's always variation and possible exception to the assumptions. The second assumption is that the scores or the measures that were obtained using a random sample from the population. And it's not always possible to achieve random samples. So it's not necessarily, although it's quite an important assumption, it might be that we can't always meet that assumption. Then the question would be do you then use parametric tests or non-parametric tests? And if you can use non-parametric tests, then they are available as an alternative, but it's also not necessarily, depending on how complex the analysis is going to be, it might not be possible to find a non-parametric test for the analysis that you need to do. The third assumption is independence of observations. What that means is that the observations that make up the data must be independent. So if you're measuring people, for example, then the people, obviously there must be differences. Each person must be different, and there mustn't be some dependency between the people. Or if you're measuring objects, the objects should be independent of one another. So the idea is that each observational measurement must not be influenced by any other observational measurement in the sample. But that again here, an exception to this would be if you're doing a repeated measures, where you're collecting data across time for the same person. So there the observations are dependent. So obviously your first measurement or your measurement for the one participant would be dependent on their next measurement and so on. So it's not always, there are designs which allow you to sort of ignore this assumption, because we do need to measure across time periods often. Okay, the fourth assumption is that the data should be, or the population from which the samples are taken are normally distributed. And that might not always be the case, but and so we test for normal distribution for variables, particularly for the dependent variable. But most tests are tolerant of violations of this assumption. And if you've got a large enough sample, the violation of this assumption shouldn't cause major problems with your analysis. So although this is an important assumption, it doesn't. There are ways of sort of getting around not meeting the assumption. And the fifth assumption is homogeneity of variance. Parametric tests work on the assumption that samples are obtained from populations of equal variances. So if you're comparing groups, for example, let's say different types of, so say, rural schools and urban schools, the variation, you want the variability of the scores from each group to be similar. And we use something called the Levene test usually to test the equality of variance. But some tests are, such as ANOVA, are tolerant of the violation, as long as the group sizes are equal. And then for t-tests, for example, they have two variations of the t statistic, one where equal variances are assumed and one where unequal variance is assumed. So the tests do compensate for this assumption with it. So there are ways of compensating for this assumption as well. So so these are the main assumptions, and then each test itself might have assumptions as well. So when you're doing a test, you would need to look out for the assumptions, the general assumptions for parametric tests, and then also for the assumptions of a specific test that you might be using. Okay. The other question is, and this relates back to the analysis plan, is what test to use. So this is I think I've shown you this figure before. This is from Field. Andy Field has got a book. It's from his book on using SPSS for statistical analysis. And it's a decision tree for choosing a test which is appropriate for the data that you have. And it's quite I think it doesn't have all the statistical tests on the table. So on the right, just to go through the table again, on the right-hand side, there's a list of statistical tests in red. And then the questions you start from the left-hand side and you work through until you get to the test that you need to use. So the first question is, how many outcome variables are there? And then it would be one or two or more. The second question is, what type of outcome variable is it? Is it a continuous variable or a categorical variable? And for the purposes of this table, we would normally treat the ordinal variable as being a categorical variable. So if the answer is continuous or categorical, that will lead you to another part of the choice, another choice. So then the third question is, how many predictive variables are there? One or two or more. The fourth question is, what type of predictive variable is it? Is it categorical or continuous? And then the fifth question is, if it's a categorical predictor, how many categories are there? So there's two groups or more than two groups. The sixth question is, if it's a categorical predictor, do you have the same participants or different participants in each category? And that would be different or the same. And then the last question is, do the data meet the assumptions for parametric tests? And that's where you would look at those assumptions and say, does your data meet those assumptions? And that will lead you to choose a particular test. So this list of tests includes t-tests, correlations, I think regression is here, MANOVA. So there's lots of repeated measures. ANOVA is here. So there's lots of different tests. Not all the tests are here on this table, though, but it gives you an indication of if you're supervising a student who needs to work out what test they're going to be using for their analysis plan, this table could be something that they could use for deciding which test they need to use. Okay, so that's from Field. Andy Field has a book he's also got some really good online stuff as well for using SPSS. Okay, all right then. How do you know that you're doing the procedure right? So that's another question. So if you're going to be using a test, how do you know that you're doing the right thing with the test? So or how do you know it's the right test, and how do you know that you're applying the test correctly? So that's there's a very good book by Hancock and Muller called The Reviewer's Guide to Quantitative Methods in the Social Sciences. And again, many of the procedures that they write about are used in the social sciences and the sciences. So it's not just these statistical designs are not just they're used by any discipline. So just because it has the word social science in the title, don't reject it as a scientist or as a health scientist. So and they have in this book, they've got a number of chapters covering different statistical procedures. So, for example, they've got analysis of variance between group designs, analysis of variance repeated measures designs. They've got correlation. They've got factor analysis. They have regression. So these are more procedures. They've got multiple regression. They've got structural equation modeling. They've got survival analysis. So these are the different, they've got logistic regression. So they've got many different statistical designs that they cover in the book. So each chapter, and we've used one of the chapters for the general research design. Each chapter has the desiderata for that particular statistical procedure. So if your student is going to be using regression, for example, let's say linear regression, there will be a chapter on that. It doesn't come up here. So this is they've got it under multiple regression here for the linear regression option. So this is the chapter. It's written by Kelly and Maxwell. And I'm not going to go through all of these desiderata, but it gives you an indication of what should be considered when you're using that particular statistical procedure. So if you want, it's like a checklist that you can go through to say, have I dealt with this? Have I dealt with this? Have I dealt with this? When I'm describing the method, the particular statistical procedure that I'm going to be using. And that some of the questions might not be relevant for the particular context, but the idea is that there's a whole set of questions that you could answer in relation to the procedure of multiple regression to make sure that you're covering all the bases. So when somebody comes to review the work as well, you can say you've covered all the questions that they might ask. And there's always going to be something which somebody picks up that's not there, but that's the part of the reviewing process. Okay, so as a tool, or as a resource, the book by Hancock and Muller is a very good option if you're going to be doing a lot of statistical work, and if you're using a particular type of statistical design, say multiple regression. This is a good resource to use for that, to kind of make sure that you're working on the right track in terms of the methodology. Okay, so moving on to specific groups, specific tests, not specific groups. There's different designs that we use. So this, for this first example, we're going to look at the independent samples t-test, which is a statistical test that we use for comparing groups. And we're going to go back to that example we looked at earlier. So the t-test, I'm not going to go into a lot of detail about the technicalities of the test. I just want to get you to get an idea of how the test works, basically. So the t-test measures mean. So what it's concerned about is, are the null hypothesis for a t-test, an independent samples t-test, there's different types of t-test, that's the other thing to note, is that the null hypothesis for the independent samples t-test is that two means are equal for the two groups. So the averages so let's say we're talking about a performance score. The null hypothesis will be that the performance score for the group that was had exposure to maths and physics is equal to the score that the students who didn't have exposure to physics and maths are the same. So there's no influence of having that exposure on your performance. So if we go back to this table here, to get to the independent samples t-test, the first question would be how many outcome variables were, and are there? And the answer there would be 1, and it would be a continuous outcome variable, because score is the mark that a student obtains is a continuous variable. The next question is how many predictor variables. The answer there would be 1, because we've got one variable which has got groups in it, which is the exposure or no exposure to maths and physics. The next question is what type of predictor is it? Is it categorical or continuous? We've got a categorical variable. The next question is if it's a categorical predictor, how many categories? And the options are 2 or 2 or more. We've got 2 groups, one group that has exposure, one group that has no exposure. Then the second last question is, if it's a categorical predictor, have we got the same participants or different participants in each category? The answer there would be different, because you either would have had exposure or not had exposure. So the two groups are made up of different groups of students. And then the last question is, does the data meet the assumptions for parametric tests, yes or no? If we assume that the answer is yes there, then we would get to the independent samples t-test. So that's how we get to that test. So that's the kind of way the table would work in terms of reaching the test that you need to use. If the answer was no to the question about does the data meet the assumptions for parametric tests, then you would end up with a Mann-Whitney test, and that's the non-parametric alternative for the t-test. Okay, so so assumptions for the t-test are that if the sample sizes are small, the variable being compared must be approximately normally distributed in the population, and the sample must be chosen randomly from the population. So that's those are some of the assumptions for the t-test. For our example, we're going to assume that we're meeting those assumptions. So when we conduct a t-test, we need to select a test variable, which in this case would be the mark, or the score that the student gets, and the grouping variable, which is the group that the student belongs to, whether they've had exposure or not had exposure to physics and maths at school. Okay, and then we set it up in SPSS using a test variable and a grouping variable, and then I've made a point here. It's not always adequate just to simply observe the difference between the means. It may be necessary to project your findings back to the population, because that's what we're trying to do with a inferential test. Okay, just also to say that there's we mentioned one of the assumptions for the parametric tests is that if we're comparing groups, that there's equal variance, and we use something called the Levene test to test for equal variance. And the null hypothesis for that test would be that the variances are equal. The variances are equal, and then we calculate something called the F statistic to estimate the difference in the variation, and that test will either be significant or non-significant, and that will determine which t value we need to use for the analysis. And you'll see when we do the output what I mean by that. Okay, the t value is calculated. The t statistic is calculated by calculating the difference between the mean of group 1 and the mean of group 2, and then controlling for the variation and the sample size for the two groups. So you can see from that formula that the bigger the difference between the means, the more likely, the bigger the t value is going to be from if you're subtracting one mean from another. And if you've got a big difference between the means, you're going to get a larger t value. So what that should indicate is the bigger your t value, the more likely you are to start saying that there is a significant difference between the means. But we still need to test that because we can't just use the t value on its own. We have to control for other factors as well. Okay, so we're going to do a test now. I'm just going to give you a demonstration, but I'm not using this. I'm going to use the old example for this one. Okay, so I'm just going to stop sharing this now. And I need to go back to the data set. So if you think about our data set that we have here, you should be able to see the data set on the screen now. Can you see the data set?
Yes, we can.
Okay, so what would you predict? What would your hypothesis be about the relationship between the student having exposure to maths or physics and academic performance? What would your null hypothesis be for that relationship? Remember, a null hypothesis is a statement of no difference. So what would your null hypothesis be for the relationship between exposure to maths and physics before joining a program and the academic, or joining an engineering program, and the academic performance of the students on that program?
Would it be something like there's no difference in academic performance between those with maths
Yes,
versus
yeah.
those that did not do.
Yes, yeah. So your null hypothesis will be that there's no difference in average mark for the students who have been exposed and haven't been exposed to maths and physics at school. And then your alternative hypothesis would be that there is a significant difference between the averages. Okay, so let's have a look at the test. How do we run that test in SPSS? Whoops, wrong window. So can you see the data file on the screen?
Yes, we can.
Okay, so I'm going to get, so when we do, thank you. So when we do the a t-test, we want to compare means and, well, we're going to be comparing means, not proportions. So the option for the t-test will be under the compare means menu in SPSS. And then we're going to use the independent samples t-test. You'll see there's other kinds of t-tests as well here, but we're going to use the independent samples t-test for this analysis. So that's because we've got two groups and we've got a dependent variable. The two groups are independent, so that's an appropriate test to use for the analysis. Okay, so I'm going to click on that menu, and then we get the independent samples t-test menu. Our test variable is going to be academic performance, so that's what we're testing. And then I'm going to use the did you learn pure maths and physics at school? And that goes, and that's our grouping variable. That's the variable that contains the group that we're interested in. Under this menu, there's a define groups option, which, and that's the reason why that's there, is that you could have a variable with more than two categories and you just want to compare two of those categories. So I'm going to define the groups, and I happen to know that group 1 is coded 0, I hope, and group 2 is coded 1. So the people who said no are 0, and the people who said yes are coded 1 for this particular data set. And I'm going to continue. So I've just defined the groups. So 0 is no, 1 is yes. You'll notice there's an option here to estimate effect sizes. So I want to keep that on because I want to see how relevant the result is. And the options here would be to have, there's not really many options here. You can have confidence interval percentages. I'm not going to change that. It's not necessary to change it. There are options for dealing with missing values, but we don't have any missing values in this data set, so I'm not going to worry about that. Okay, I'm not bootstrapping because we've got a big enough sample. Okay, so I'm going to click OK, and that's going to generate some output. So I need to toggle screens. Again, go here. Oops, going to the wrong place. Share. Okay, so you should see an output file now. Can you see the output?
Yes, we can.
All right, so this output file, there's a couple of tables here. So we're going to focus first on the averages. So this is the summary statistics for the two groups. So the average score for the students who had no exposure was 8. And I'm not going to worry about the decimals. And then the average score for the students who had exposure was 10. So looking at those averages, it looks like the group that said that had exposure is a little bit higher. It's definitely higher in absolute terms, but we don't know whether it's statistically different. We can't just assume from those numbers because we have to take into account the standard deviation. And if there's a lot of standard deviation for the two groups, they might overlap. So that might give us an indication of so we need to do a statistical test to see whether those two averages are actually different, whether they're statistically different, even if we can't just rely on the absolute numbers there. We need to do a test to see whether they are statistically different. Okay, so the first thing we look at here, you'll see there's two t-values. There's a t-value, this is the statistic that we're going to use. So the first t-value is for equal variance is assumed. The second t-value is equal variance is not assumed. So I need to decide which of these two numbers I'm going to be using. And I use this Levene's test for equality of variances to decide which test I'm going to use. So this test here is saying the F statistic is pretty high and the significance is low. So this p-value, the significance level is a p-value. So the null hypothesis for this test would be that the variances are equal, but the variances are different. If I look at these numbers here, they're different, and the sample sizes are quite large. So this test is telling me that those variances are not equal. So I'm rejecting the null hypothesis here that the variances are equal because my p-value is less than the alpha level of 0,05. Remember, we set that alpha level as a hypothetical value, which we set to compare the p-value to when we do statistical testing. So my p-value is less than 0,05. I'm going to reject the null hypothesis that the variances are equal, and I'm going to use this equal variances not assumed t-value. Okay, so just a more stricter calculation of the t-value because the variances are not equal. So I'm looking at this result here now. This is my result for the t-test itself. And I'm using the non-equal variances t-test. So for the t-test, the null hypothesis is that the average scores for the two groups are equal. I'm getting a relatively high t-value. There's no right or wrong value for the t-value, but it's quite this. I can see, knowing what t-values can be, I can see that this is quite a high value. And the p level, this is the significance level. The p level is 0.001, and that's less than 0,05. So I can reject the null hypothesis that these two means are equal. So I can say, and to interpret what the difference is, you have to look at the means. So my test tells me that the two means are different, significantly different. And I'm going to use the two-sided p-value because I'm not predicting that one group will be higher than the other. I'm just predicting a general difference between the two. And from this, I would conclude that the group that have had exposure to physics and maths in school are performing better than the group that hasn't had exposure to physics and maths at school. So that's what I would that's how I would interpret that result. There is a statistically significant result between those two averages. If this p-value here was greater than 0,05, I would not be able to reject the null hypothesis, and then I would say they were equal, but that's not what this test is telling me to conclude. So basically, from this, you would say you would be able to conclude that the group that is exposed to maths and physics in school perform better on the engineering program. And then what that would imply is that you probably need some kind of intervention for the group that's not doing so well, the group that hasn't. So they'd need some kind of bridging program or something to help them get up to the same level as the group that did have exposure. Okay, so that's how an independent samples t-test would work. It's very straightforward. It's a very simple test in terms of how it works, and it's a very simple test in terms of interpretation. Yeah, so that's a comparison of means for two groups. Okay, so I'm going to stop sharing this. Are there any questions about this test at all? Oh, yeah, I forgot to mention the effect size. Sorry. So in this table here, there's a measurement of the effect size. So this is we normally use Cohen's d there's different measurements of the effect size, and you'd use there'd be different sort of reasons for using these different options. I'm going to focus on the Cohen's d because that's the one we commonly use, and this would be when you use the Cohen's d, there's a sort of range of values which would indicate whether it's a weak, moderate, or positive or high, strong effect size. And in this case, the 7.34, the 0.7.34 would indicate that this is a strong effect size. So over and above the significant result that we're getting here, we're also getting a strong effect size for that difference. So it's another statistic that we use to emphasize the importance of the difference. And that would mean, you probably do need to have some kind of decision making around these scores that the different groups of students are getting, because there is an impact of the exposure to maths and physical science in school on the performance of the students. So this is kind of telling us that that's an important result, and that because it's an important result, it might mean that if it wasn't an important result, then you wouldn't worry about it so much. But because it is an important result, you might start thinking about what could be done to solve that problem. Okay, so that's the independent samples t-test. Any questions about the test at all? Okay. All right. So I'm just going to go back to this window here. Okay, there are other tests here as well, which I'm not going to run, but I just want to talk about them briefly. So there's also the paired samples t-test, which is if you are trying to compare scores over time, for example, for two groups or two time periods, then you would use the paired samples t-test. That's so if you follow that table with the stats decisions, there's a question towards the end which says, if you've got two groups, or do you have the same people in the group, or do you have different people in the group? If you have the same people in the group, then you would use a paired samples t-test. So that's kind of measuring things over different time periods. It might be a before, after kind of design. Okay, there's also one sample t-test. So if you have a single value that you want to test against a known value, then you can use the one sample t-test. So let's say, for example, you were wanting to calibrate a machine, for example, and you know that the range, let's say, for example, you take 6 measurements on the machine, and you know that those measurements should be within a certain range. You can test that, you can test your data against that value, that expected value that you want to get. So there's different tests there. We're going to come to the ANOVA now. So we're going to go to that window now. Right. So that's then the question is, how would you write up the results for a t-test? So one of the problems that students have is writing up the results of their statistics. So there's a book by Palant called the SPSS Survival Guide. And in the chapters, so Palant covers a number of statistical tests. And in the chapters when she's gone through the explanation of the tests and explained how they work and explained how to run them and to get the output, there's usually a section at the end which explains how to write up the result. So, for example, this is an example of writing up an independent samples t-test. The example is different here, but if you were writing up for the example we've just used, you would say an independent samples t-test was conducted to compare the performance scores for students exposed and not exposed to maths and physics. There was a significant difference in the scores, and then you would give the mean and the standard deviation for the group that was exposed and the mean and the standard deviation for the group that wasn't exposed. And then you give the t-statistic, the degrees of freedom, and then the p-value for the test. And then you can also report on the effect size as well, which indicates, in this case, we would conclude that there's a large effect size for our study. So that's an example of how to report a t-statistic. And obviously the interpretation will depend on what the result is and what the size of the statistical result was. Also, just to say that it's also important to report no differences. So sometimes when a result is no statistical difference, students get agitated and they get worried about having no meaningful. They think it's not a meaningful result, but a result of no difference is just as important as a result of a difference, because it's telling you that if you thought there was a relationship there and there isn't a relationship there, that's also meaningful. It's not as exciting as having a difference, but it's certainly still adding to the body of information about the variables that you are looking into. Okay, so this is an example of a paired t-test. So, for example, if you were wanting to measure if there's a change in anxiety scores from time 1 to time 2. For the same participants, that's where we'd use the paired samples t-test. So we've got one categorical independent variable, which is time 1 and time 2. And then we've got one continuous dependent variable, which for this example would be anxiety scores. And it's very important for these kinds of data sets to pair the data. I think we've spoken about that before. You don't want to, you have to make sure that the data for the first person is on the same line and not mix up the responses. Sometimes people design studies where they collect data and they don't monitor who's given the response, and then they go back again and they measure again, but they can't link the second set of data to the first set of data. So all you can do is you've got a blob of people that you're analyzing before and a blob of people that you're analyzing second, but that breaks the assumption of the data points being independent because they are related. The only way you can analyze it is two separate groups. So you've got you'd have your one group data for your one group and data for your second group, and you'd use a grouping variable of group, but you're not pairing the data, and that breaks the assumption of your measurements being independent because you've measured the same person twice. You've got data for the same person in the same data set, and it's not paired, and that breaks that assumption for the parametric test. So you don't want to do that. Okay, and that does happen quite a bit actually. We get quite a few projects where the students don't pay attention to the pairing. Okay, so just bear that in mind if you are doing any kind of paired sort of designs. Okay, another test we can use for comparing groups. So we don't always have two groups. Sometimes we have more than two groups. So we need a test which will allow us to analyze for more than two groups. So this is, we're going to use analysis of variance for this. We use analysis of variance to compare the means for more than two groups. So this is an example. So you might say, is there a difference in optimism scores for people who are in 3 different age ranges? So you've got one categorical independent variable, and you've got one continuous dependent variable. And then there's 3 or more groups, and there's different people in each group. So that's, if your data meets those characteristics, then the one-way ANOVA analysis of variance is the appropriate test to use. How do you check that you are meeting all the requirements? This is the chapter from by Clockers on analysis of variance between group designs from the book about evaluating statistical research. And you'd need to kind of make sure that you're meeting these different, or that you'd need to kind of go through the set of desiderata to make sure that you are covering the different dimensions that you need to use. Okay. Some of these things are, I'm not going through each of these individual things, but it looks quite complicated. But it doesn't have to be. Some of them might not be that critical for the work that you're doing, and most of the time you'll probably be meeting the sort of desiderata that are expected for the tests. So it's probably not as difficult as it makes it seem with this very long table here. Okay, so with an ANOVA, you want to determine whether one or more discrete factors has an effect on the mean of a dependent variable, and to see whether the effect of one factor depends on the value of another factor. That's if you're doing a sort of a multiple ANOVA, it's not a MANOVA, but if you're using more than one predictive variable. We're only going to use one in the example. And to compute an ANOVA, you need to input a dependent variable and a factor variable, at least one factor variable. The way that ANOVA works in terms of formulas is you estimate within group variability. So you've got 3 or more groups, and you want to, the way the ANOVA, the F statistic for the ANOVA is estimated is you calculate within group variability, And that's the variation within the group, so within each group in your sample. And then I'm not going to go through all the details here, but it just explains here how you do that calculation of variability. And then you also calculate the between group variability. So that's how much the means differ between the groups. And there's the formula, there's the explanation of how those means were calculated. And then you also calculate degrees of freedom, which is the number of groups that you're working with. That's for the between group. Within group, you also calculate the degrees of freedom, which is based on the size of the groups. And then you divide the sum of squares calculations by the degrees of freedom to get the between group variability. And then the F statistic is estimated based on the within group variability and the between group variability. I'm just going through this quite quickly. So the F statistic is calculated by the between group mean square and the within group mean square. And then you can also use post hoc tests in the ANOVA to establish which groups are different to one another. So when you're testing groups, the ANOVA in total tells you whether there's a difference between the groups, but it doesn't tell you which groups differ. It just says overall there's a difference. So you need to do what we call post hoc tests to establish where the differences lie. And then we use the equal variance comes into play with the ANOVA, because we want to, if we've got unequal variance, we use different post hoc tests to if we have equal variance. So again, that assumption of equal variance can be accommodated with the ANOVA. So we can manage that unequal variance within the ANOVA procedure. We don't have to, it doesn't stop us from using the ANOVA if we have unequal variance. We just have to be more cautious with the interpretation of the post hoc test, or we just use a different kind of test. Okay, so how do we run a ANOVA? I'm just going to load a different data set here. I want to change data sets. I'm just going to close this down. And I'm going to open a new data set. Okay, so I'm just going to... Okay, it's quite difficult to have a data set which does everything that you need it to do. So I just have to jump around a bit. So this one here, where am I? Okay, so we're going back to SPSS. Okay, so for this example, we're going to look at analysis of variance of job category by the salary that the person obtains for the job category that they're in. So this data set has got a lot of data points in it. There's over 400, I think, data cases in this file. Sorry, can you see the data file on the screen?
Yes, we can.
Okay, good, thanks. Okay, so what we're going to use, the job category variable has a number of categories. So it's clerical, technical, and so on. So there's a number of job categories that are in the data set. And then we're going to look at the salary that the person obtains for that particular job category. So the grouping variable has multiple categories, and the dependent variable is a numeric variable. So we're going to use this one-way ANOVA procedure, because we're just using it's a simple ANOVA that we're using here. So that's the option. The dependent variable is going to be current salary. And then the factor is going to be employment category. Okay, we don't need to put groups in here because we're going to be using we're going to be using all the groups. Okay, so we would probably predict our null hypothesis here is that the salary, the average salary is going to be equal for each of the employment categories. And then we're going to either accept or reject that null hypothesis based on the result that we get for the ANOVA. I'm just going to check here. I don't want to do anything there. Okay, so under the ANOVA menu, there's a post hoc option, which is going to help us identify which groups differ. And there's two types of post hoc tests. There's equal variances assumed and equal variances not assumed tests. So I'm just going to use Sheffy as a common equal variances assumed test we use, and I'm going to use Dunnett's T3 for there's different reasons why we use these tests, but these are common ones that we might use. Okay, I'm going to continue there. You can use other ones as well, but you don't necessarily need lots of different types of tests. Two is enough. Options here, I'm going to use, I'm going to run the descriptives because I want to get the means for each group. I'm not going to worry about fixed and random effects because I've only got a fixed variable. I'm going to run the homogeneity of variance test because I want that to, I want to see what the variance is. And I'm going to run the Brown-Forsyth test. This is a test which tests for differences using, assuming that there is unequal variance. So that gives us a more robust estimate of the difference between the groups. I'm not going to run a means plot. You could if you want, but it's not really something that I want to get from this at the moment. Okay, I'm going to continue there. And then that's all I need at the moment. So I'm not going to bootstrap. It's not necessary. Okay, so I just need to toggle the screen here. Stop sharing that one. I hope this has come out right. Okay, so this is the result from the ANOVA. So you'll see we've got about 7 or 8 groups of of job types, from clerical through to technical. Okay, there's very few people in some of the groups. So our groups are very unequal. We normally wouldn't want our groups to be such unequal sizes for an ANOVA. So you can see the output on the screen. Just let me check.
Yes, we can.
Okay, right. Okay, so what this is showing is that, so I've run the analysis anyway because this is a variable which has a number of groups, but we wouldn't normally want such small groups compared with such large groups because that can skew the so the bigger groups would tend to dominate in the distribution, and the small groups could give us misleading results. But you can see what it's done is it's rated the groups from lowest to highest average. It might be that they were in that order, or that they were, because normally when people classify job categories, they might do them from lower level to higher level. So that's probably what we're seeing here. The standard deviations you can see are quite high, which are typical for income or salary-based figures. There's some so for example, the small group of technical people have very high standard deviation, and that can be very typical. Variables like income or salary can be very, very variable. Okay, so those are the descriptive stats. The Levine test for homogeneity of variance, which I'm basing on the mean here, is significant. So that means that we don't have equal variance between the groups. And you can see from these figures here, I'm just using the standard deviation as an indication, or if you use the standard error as an indication of variation. There's a lot of variability in the variation for the different groups. So that's why the Levine test is significant. So we'd need to use the non-equal variance post hoc tests for the analysis. The ANOVA summarizes the between group and within group variation, and we're getting a significant result for that ANOVA. So what that's telling me is that overall, there is a significant difference in the means for the mean salary for the different categories. So if you think about that null hypothesis, that the salaries are equal for each category, each job category, I'm going to reject that null hypothesis based on that result, this p-value. We're getting a high F value. That's a very high F value because the difference between the means, the difference between the groups and within the groups is quite large. So that's why we're getting a large F statistic, and it's a significant result. So I'm going to reject that null hypothesis that the mean salary is equal for the different job categories. To understand which ones are higher and lower, you can go to the mean. So you can see technical, for example, has a much higher average than, say, clerical, which makes sense. An office trainee, they're very similar. Technical is much higher, and the MBA trainee is also much higher salary. Exempt employee is also much higher. So there's a range of average salaries here, and that's why they're coming up as being significantly different. This is the effect size, which is eta squared is the normal one we would use here, and that's quite a large value. So it's quite a meaningful difference that we're seeing. This is the robust test for equality of means, which takes into account the unequal variance, and that's significant. So I can be confident in the conclusion that there is a significant difference in salaries. And then this is the post hoc test where we get multiple comparisons between the different kinds of job categories. So you can see, for example, I can see from this table that clerical office trainee and security officer are not different from one another, but clerical is different to college trainee, exempt employee, MBA trainee, and technical from the significance in the from the significance column. And if you look at the difference in the mean, you can see that clerical is lower because the clerical minus college trainee gives you a minus figure. So that's telling you that the clerical salary is lower than the college trainee, exempt employee, MBA, and technical employee. So that's then the ANOVA also gives you a summary table, which is quite useful, which gives you the subsets of the salaries based on the different categories. So technical is the highest and stands out on its own. And then you've got a grouping of MBA trainee, college trainee, and exempt employee. And then you've got a grouping of clerical office trainee and security officer. So in terms of the salary groupings, you could group these are the three lowest, then the three middle, and then the highest. So the ANOVA gives you quite a lot of detail about if you are concluding that there's a significant difference in the salaries, it also helps you identify where the differences lie. And that's a useful sort of analysis to be able to do. Okay. So are there any questions about this test? Has anyone ever done an ANOVA before? Okay, right, and then presenting the results. How do you write up the results for ANOVA? Again, this is an example from Palant from the ANOVA chapter. There's different, Palant has chapters on different types of ANOVA. So this is on the sort of simple one-way between group ANOVA. And it's a one-way, just describing it as a one-way between groups analysis of variance was conducted. And the example we've just used, it would be to explore the impact of job category on salary, on current salary. And then subjects were divided into maybe 7 groups, and that would be trainee, I can't remember what the other ones were, the different employment groups. And then you would report on the significant, you'd report on the different between within group scores, and then you might give the mean scores for each group. And then you might talk about the difference. You would say, for example, that 3 groups were grouped together. There were 3 middle sort of salary groups, and then there was 1 very high salary group from that, based on the analysis that we've just done. So that's an example of how you would write up the results. Again, if you're supervising students that need to report on an ANOVA, this is the kind of resource that you can use to help them, to guide them in terms of writing up their finding. Okay, and then obviously in terms of, you need to kind of move beyond just reporting the result. You would want to, if you're identifying that there are these sort of significant differences in salary according to job category, you then want to have a debate about what that means in society. So is it So are the salaries reasonable for that job category? Should something be done to make them more equal, for example? That's where the kind of your findings show that there is a difference, and then you would then have to have a discussion about what the meaning of that difference is and what should be done about it, if anything. If it's felt that something needs to be done about it, what should be done about that difference in salary? Okay, so that's again comparing groups. The non-parametric equivalent to the one-way ANOVA is called a Kruskal-Wallis test. So if you can't use the ANOVA, if you don't meet the assumptions of using an ANOVA, there's a non-parametric alternative called the Kruskal-Wallis test, which if we get time, I'll show you how that works quickly. Okay, another kind of ANOVA is a repeated measures ANOVA. So sometimes in health sciences, for example, students will they'll apply treatment to patients, and they want to see if there's a change in the patient's pain levels over time. So they'll measure pain level, or even they might use, they use different, so like the chiropractors, for example, use something called an algometer, and then they also use a questionnaire which measures pain more subjectively to measure pain levels and sort of flexibility of patients getting treatment. And if you want to see whether there's a decrease in or an increase in flexibility and a decrease in pain, you would use the one-way repeated measures ANOVA for that analysis. There's a non-parametric alternative called the Friedman test. For this kind of design, you need one categorical independent variable, which is the time periods, and then one continuous dependent variable, anxiety, which in this case is anxiety, but it might be your pain level or some other kind of your measure of flexibility, for example. You can also do mixed within between group ANOVAs. That's a common design that we often have to help with analysis on. And that's where you have multiple groups that you're comparing. So you might have a control group and an experimental group, and you have the time period. So you actually have two independent variables. One is the grouping variable, one is the treatment versus control variable, and the other is the time variable. So you measure whether theoretically the control group should stay the same over time, and then the experimental group should change in some way. So that's so there's lots of different ANOVA designs that you can use for studies. Okay, then moving on, there's we also can use so our research doesn't always involve comparing groups. You might want to test for a relationship between variables, and that's where we need to use something called correlation. So it's a different kind of test using different kinds of variables. And that's a common test. It's quite a common analysis to use correlation, because you often want to know whether variables relate to one another. And if you go back to that idea of the theoretical proposition, sometimes the variables we're measuring for those theoretical propositions will be interval variables. So an example would be is there a relationship between age and optimism scores? So the idea here would be, excuse me, if you, does age influence optimism? So is it could it be the younger you are, the more optimist you are, or vice versa? The parametric test we use for that is the Pearson's product moment correlation, which we refer to as the Pearson's correlation coefficient. There's a non-parametric alternative called the Spearman's rank correlation. And to do this, we have two continuous variables. One of them might be considered independent and the other might be dependent. So in this case, your age could influence your optimism, but your optimism doesn't affect your age. So in this case, age would be a sort of independent variable and optimism would be a dependent variable for that relationship. So you could have one or maybe even two samples with scores where you've measured these variables. Okay, this is an example. How do you do your checks to make sure that you've got the right data and that you're using the test correctly. This is a chapter by Osborne on correlation from the text about evaluating quantitative research. So these are the desiderata for the correlation procedure. I'm not going to go through these, but if you're doing a correlation, you can have a look at that chapter, and that will give you an indication of what you should be looking for when you're doing a correlation. Again, it looks quite complicated, but it doesn't have to be as complicated as this Max suggests it might be. This is just a very intensive kind of focus on the things that you need to consider. Okay, so correlation coefficient, a correlation measures the strength of a linear relationship between two variables. The null hypothesis would be that there's no linear relationship, and the alternative hypothesis would be that there is. We can calculate an equation which estimates the relationship between the dependent and independent variable. So, and I'm not going to go into the formula, but we get a Pearson's R correlation by using the formula below, which is based on the values and the mean and the relationship between the two variables. So x is the value for variable x, and the mean is the mean for those values, and then y is the value for variable y, and the mean we can also get a mean for the values that measure variable y. N is the number of cases, and S is the standard deviation for the two variables. So the correlation coefficient is based on the sum of the interaction between the two variables in relation to their values and the mean of those variables. So the correlation coefficient ranges from +1 to -1. So if you get a correlation coefficient of more than 1, you've made or less than -1, you've made a mistake with the calculation. But again, the computer's doing it for you, so you don't need to worry about it. Should do it correctly. And then the absolute value of the coefficient indicates the strength of the relationship. So we talk about if a correlation coefficient is less than 0.3, then it would be a weak correlation. If it's 0.3 to 0.5, then it's a moderate correlation. If it's more than 0.5, then it's a strong correlation. We can test the null hypothesis that the population coefficient is 0 using a t-statistic, and so we can estimate a statistic for the correlation coefficient, and we're going to do an example now. And we don't use correlations for nominal variables. I think we mentioned this. No, I haven't mentioned that. So if you can't do correlation with categorical variables, but there is a procedure called the point biserial correlation, which we can use for dichotomous variables. So if you've got a dichotomous variable and an interval variable that you want to correlate in inverted commas, we can use something called the point biserial correlation. But we normally would use what we normally do is we normally do a Mann-Whitney test, for example, if we've got a dichotomous variable and an interval variable. So, and then the assumption for the parametric correlation is that for testing the hypothesis around the population correlation coefficient, we would assume that the two variables together would have a normal distribution. So again, it's that assumption for the parametric test. And then importantly, a correlation doesn't mean there's causation between the two variables. So if two variables correlate, it doesn't mean to say the one causes the other. It just means that they have a relationship, but it's not necessarily a causal relationship. Okay, so here's some possible relationships. We've got age and beginning salary, and we've got beginning salary and current salary, and we've got age and current salary, and we've got education level and current salary. So what would you predict for these correlations? If you think about age and beginning salary, would you expect to see a positive or a negative correlation between those variables? And we're going to look at some data now, which gives us the answer to that question. I think for beginning salary and current salary, you might expect those to be correlated, because theoretically, the higher salary you start on, the higher your salary might be now. Age and current salary could be related, might not be related. We don't know. It might be that the older you are, the higher your salary is. Theoretically, there should be possibly a positive correlation there, because the longer you've been in the job market, the greater your salary might be. And then education level and salary are usually positively correlated. So the idea there is the more years of education you have, the higher salary you can probably command. So based on those relationships, you would expect to see, you don't know for sure, but you'd expect to see some kind of correlations there. So we're going to look at that now. So we're going to run some correlations in SPSS. I just need to check which variables I'm working with. Okay, so that's fine. Okay, so it's going to stop sharing now. I'm going to go back to SPSS. Okay, so for correlations, you should be able to see the data file on the screen. Can you see the data file on the screen?
Yes, we can.
Okay, so for the correlation procedures on the menu, there's a correlate option on the menu here, and we're going to do bivariate correlation. So we're going to look at these variables just in sets of two, which is we call that bivariate analysis. So we're going to use the bivariate correlation to test the correlations between the different variables. So the variables I was looking at were beginning salary, age of employee, current salary, and education level. So these are all kind of interval variables which we're going to look at for the correlations. I don't think there's many options here. I'm not going to worry about that. Yeah, so you'll see there's different correlation coefficients. The Pearson's is the parametric correlation. The Spearman is the non-parametric correlation, but I'm not going to run that now. And then it's asking me if I want to flag significant correlations, which it's a good idea to do that, because then that sort of highlights them for you. You can also ask it to just show the one part of the table, which makes it easier to interpret. So I'm going to take this off. The diagonal is the correlation between the variable and itself, which will give you a correlation coefficient of 1, which is not very helpful. Okay, so I'm just going to click OK there, and then I'm going to go back to the just stop sharing, go back to the other window. This is the output window. Okay, so this is the correlation table for the 4 variables of interest. So the table has a correlation coefficient, which is the first value. The second value is the p-value. This is the significance level of that correlation coefficient. So what we don't see here is the t-statistic, which is used to estimate the significance of that correlation coefficient. And then the n is the number of cases, which we're not, that's going to be the same because we don't have any missing data for this data set. So if you look at the correlation here, there's a very strong correlation, 0.880. It's a strong positive correlation between current salary and beginning salary. So what that's saying is that if you start out with a higher salary, you're going to end up with a higher salary later on, which makes sense. It doesn't necessarily, it's not going to be the case for every person who enters the job market, but there's a very, very 0.88 is a very strong correlation. So that's the highest correlation in the table. The next highest correlation is between current salary and education level, which is also a very high correlation, 0.661. It's a significant correlation, and it's significant at the 0.01 level. So that's also a sort of very meaningful kind of correlation. So what that's saying is that the longer you've had for education, the higher your salary is going to be. So we'd kind of probably expect that from literature and publication and so on, but this is confirming it for our data. So our data would then confirm what other people have shown. So you either confirming or maybe refuting what other researchers might have shown with that information. Also, education level is also strongly correlated with beginning salary, which would also make sense. The higher your level of education, the higher the job type you might be getting, and therefore your salary would be higher as well. So this is showing the strong relationship between education and salary. And then there's a negative correlation between age and level of education. It's a weak correlation. So what that's saying is that the older the person is, the lower their education level relative to everybody else in the sample. So that is, I think, it's not an unexpected result, because there is, although you might think that older people would be more educated, the access to education has got better over the years. So younger people today have much access to a higher level of education than older people in the population had sort of 30, 40 years ago. So that's not an unexpected result, although you might normally think that there would be a positive relationship between age and education. Access to education has become stronger over time, so the younger generation would have a better education level than the older people in the sample. So that's not unsurprising to me, based on what I know about the sort of education and labour market. There's no relationship between beginning salary and age of employee. So that's another interesting finding that, there doesn't necessarily need to be a correlation there. And this is showing that there isn't. So age, there's no kind of linear relationship between age and beginning salary. So that's a non-significant correlation. And then there's a weak negative correlation between age and current salary. So the older you are, it's a very weak negative correlation. So the older you are, the lower your salary would be for relative to the rest of the sample. So that's the correlation coefficient. It shows the relationship between the linear relationship between sets of variables. If we were doing, I'm just going to stop. If we were going to plot these correlations, we'd use something called a scatter plot, an XY plot, usually with a linear line through that distribution. So I'm going to show those on the, I'll stop sharing that. And let's go to the thing here. Yeah, okay, so this is just, I think we've discussed that. Yeah, if you're presenting results from the correlation, this is another example of how to present results from a correlation. So you might say the relationship between education level and current salary was investigated using a Pearson's product moment correlation coefficient. And then you would say that there was a strong positive correlation between education level and current salary, and then you give the correlation coefficient, the number of cases, and the p-value. And then you would say with higher levels of education being correlated with higher salary, for example. So that's how you would write up the result from the correlation. And then again, interpreting that, you need to move beyond just describing what you found to what that means in terms of the context that you're working in. So what that result would suggest is that the better educated the population, the better the salary might be. And that's or within the context that you're working in. Okay. You can also, when you represent if you've got multiple correlations, it's a good idea to use a table. So this is representing the correlations in a table, which is more efficient than writing out each one separately. And this is an example of presenting correlations in a table, then you would describe them. And you notice that they're only showing the correlation coefficient with the level of significance. They've removed this is the correlation coefficient. They've removed the p-value and the number of cases, because that should be the same for all of them anyway. So it's a much more concise way of showing the table. And then if you're plotting correlations, usually we would use a scatter plot with a linear line through that scatter plot showing the relationship. So this is an example of education level and current salary. It's a bit sort of blocky here because the education level, although it's an interval variable, there'll be lots of people on each interval point, and it shows that the salaries are spread. So, for example, if you've got 15 years of education, for example, the people who've got 15 years will be spread. They will have different salary levels. So that's why they're kind of climbing up or that's why they're sort of populated on top of each other. But you can still fit a line through that distribution, and that gives you the linear relationship between the two variables. Okay, this is not this doesn't look this is not as random as a scatter plot would normally look. So this is more like, these are just examples of more random kind of scatter plots, where the data is more sort of randomly distributed across the two variables, and you would plot a line through those different distributions. Okay, the problem with correlation is that we can only analyze two variables at a time, and we sometimes need to use more complex statistical procedures if we want to measure the relationship between multiple independent variables and a dependent variable. So correlation is a good technique to use, but it's limited because it's a bivariate procedure. It doesn't allow us to look at more than two variables at a time. So we need a more complex procedure. In this case, we're going to use, I'm going to give a demonstration of linear regression, which is a more complex statistical procedure than correlation. So this is just an example where what we would have here is multiple independent variables, usually continuous variables, but I'm going to use dummy variables in the example that we're going to use now. And then you've got one dependent variable, and then so that allows us to look at multiple variables together. And I'm just going to go here. This is not moving, stuck. Let's try this again. Okay. I haven't lost the link. Okay, again, how do you make sure that you are including everything that you need when you're dealing with a particular procedure? This is the example from the text about multiple regression desiderata. So there's a range of things that you need to account for when you're using regression. Some of them are very straightforward. So, for example, there's a thing here about variable selection techniques are justified. It shouldn't be difficult to do that. So you shouldn't have to. Some of this is more. It looks complicated, but it doesn't have to be as complicated as that. Okay, so regression takes the form of a model. So I'm not going to go through this in extensive detail because I think it's easier to explain when we look at the results. But we use a model where y is the dependent variable and the x1, x2, x3 are the independent variables that we are measuring. Because we've got multiple independent variables, we can't, we could have a simple model where we only have one independent variable, but because we've got multiple variables, we need to add those into an equation. So we use a formula. Well, we have a formula. This is an example of what we're going to use for the model. So we're going to look at current salary in relation to age, education level, gender of the participant, and beginning salary. And I'm going to put those three in. So we know that all three of these variables could influence current salary, but we want to establish which one of those has the most impactful effect on current salary. And then I'm also going to use beginning salary in a slightly different way, just to show you that we can develop models in a different way. Yeah, so I'm not going to go into this detail, but this is the technical stuff. I'll talk about this when we look at the result. And then also this, I'll tell you what the R-squared is when we look at the result. And then I'll also tell you about these beta coefficients when we look at the result. Yeah, so this is all the technical aspects of the regression, but I don't want to overload. I've probably already overloaded you with technical stuff. So I'm going to just go through, I'm going to explain this when we get to the actual model itself. Okay, so we're going to test this model in the regression. So, and that's what we're doing there. I'm going to use the linear regression, and that's fine. Okay, so I'm going to go back here. All right, so I'm going back to SPSS. Okay, so for the regression, if you go to the Analyze menu, you'll see there's an option here that says regression, which is nice and easy for us to understand where to find it. And we're going to do a linear regression because I know there's correlations, because I've done correlation analysis, and I know there's significant correlations between education and beginning salary and current salary that allows me to use those variables in a regression model. So I'm meeting some of the assumptions that we need to use for regression. I'm also going to use, we normally wouldn't use dichotomous, well, we normally don't use categorical variables in regression, but there is an exception. If you've got a dichotomous variable, you can use it in regression. And similarly, you'll see that there's an option here, binary logistic regression. So theoretically, a regression has a interval variable as an outcome, but you can do regressions with categorical outcome variables. So binary logistic is where you have a dichotomous outcome, and multinomial logistic is where you have a more than two category outcome variable for your regression. So there's always options. There's lots of different options here for different kinds of designs. So if you're doing a medical experiment, for example, where your result is, where your outcome variable is successful treatment, unsuccessful treatment, you can use a binary logistic regression to explain those why those outcomes might occur. So there's always alternatives, but I'm going to use the linear, which requires us to have a numeric or an interval outcome variable. So the linear regression is the option I'm going to. My dependent variable is going to be the current salary, because I want to predict current salary based on a set of independent variables. I'm going to use sex of employee. I'm going to use age of employee, and I'm going to use educational level as independent variables. So I know that each of those variables has some kind of relationship with current salary. Then when you do a regression, you can do a multiple stage regression. So I'm going to go next here, and I'm going to put current salary, beginning salary in as a second level of the model. So you can build different kinds of models when you are doing regression models. I just need to be careful here now. So I'm going to do collinearity. I need the Durbin-Watson. Okay, I'm just going to choose some statistics here so that it helps me explain the model to you. I can do this case-wise diagnostics. Choose those. I'm not going to, I can do plots. Continue. I'm just choosing some figures which will help us interpret the regression. I'm going to save Malinobis distance and Cook's, and I think that's all I need here. Don't worry about that. And then that's okay. Okay, so those are, I think that should give us what I'm looking for. when you run regressions, you can also enter the variables in different ways. I'm just going to use a sort of fairly straightforward way at the moment for this example. And then, so this, what I'm doing here is I'm telling the SPSS to run a model with 4 predictor variables and the 1 dependent variable. And I click OK, and then I should get the result here. I just need to toggle between the screens. Okay, so wrong window, sorry. Okay, so this is the output window for the regression. So this overall R-squared value summarizes it's in a sense, it gives us an indication of how strong the model is in terms of so what we're trying to do here is we're trying to explain the variation in current salary using a set of predictor variables. So we're saying we know that there's variation in current salary. How do we explain that variation? What variables could we use to explain? And it could be things like education level. It could be things like the age of the person who's getting the salary. It could be the sex of the person getting the salary. So that's we've got a model testing that. And this is telling us what amount of variation we're explaining in the outcome variable. So this can be converted to a percentage by multiplying by 100. So the first model explains 48.7% of the variation. The second model explains 80% of the variation, which is a good level of explanation. Usually for social kind of designs, we get quite low levels of explanation here. So that's the one statistic which is important. So when you're reporting as well, you would always report an R-squared value for a regression, because that tells the reader how sort of what level of explanation the model is providing. Okay, the second, this Durbin-Watson statistic is also good. It's sitting at 2, which is the sort of a good value. So if you're looking for Durbin-Watson, that would be considered a good figure there, and that's speaking to the issue of it's kind of indicating that the data has got a good balance, I would say, in terms of the distribution of the variables and so on. Okay, this F statistic here and the test, this tells us whether that R-squared value is equal to 0 or significantly higher than 0. So this is telling me that we have a significant model, and this is the kind of overall statistic that we use to report this. It's for the regression in terms of accepting or rejecting the null hypothesis regarding the regression. So these are good results. They're significant. If this was higher than 0.05, then we wouldn't be able to. Our model would not be doing a good level of explanation, basically. So in this case, the variables that we're using are explaining the variation in current salary well. Okay, then we go down to this table here. This table gives us an indication of each individual variable in relation to the dependent variable. So there's a T statistic here and a significance level. So the variables with significant results are the variables which are significantly impacting on the current salary. So sex of the employee is significant and education level is significant. We know from the correlation that education level is well correlated with salary, and it's showing up as being significant in the model here in a positive way. So this beta coefficient here is, so when we report on the regression, we would say that education level has a significant relationship with current salary in a positive way. And because what the regression does is it takes the original measurement, which was unstandardized, and it standardizes the measurements into similar kind of things. So we've got sex of employee, which is basically measured as a 0-1. We've got age, which is measured as an age, and we've got education level, which is measured as a number of years of education. So each of those 3 variables is measured in different ways. the regression standardizes those coefficients into using a standardization process. And then it allows us to kind of look at each one in an equal way to say which of these variables has the most impact on salary. So if we look at this model here, the highest coefficient is education level, which is positive. So that, and what we can say from this is that if we improve our education level by 1 unit, we can increase our salary by 0.582 units. If we go from being male to female, we're going to reduce our salary by 0.244 units. So because the relationship between sex and salary for this sample is that the male salaries are higher on average than the female salaries. So this is telling us that if we increase if we move from being male to female, the salary is going to decrease by 0.244 units, controlling for these other variables. Okay, so there's 2 significant variables there. If we add in the beginning salary, then that is also significant, and that actually has a very marked impact on the model. So if we add in beginning salary, that is the most significant, that becomes the most significant predictor of current salary. Whether this is a good model or not is another question. And then, yeah, sex of employee is no longer significant, but age and education level still are, but they're much less impactful than beginning salary. So, but this is not necessarily a good model, and I've used it as an example to show that sometimes the way you put variables in can have a big impact on the result. So I think the more meaningful result will be this first one, where you've got education level as being a strong predictor of salary. And obviously beginning salary is as well. But in fact, your education level might impact your beginning salary. So the model should more rather be that this beginning salary goes into the first level, and then the other variables come in the second level. But that's it might not make much of a difference. So when we do regressions, we also need to look into what they call collinearity. So sometimes the independent variables can interact with each other, and that causes problems with, so for example, education level and salary, beginning salary might be interacting and causing issues with the data. So with the coefficients. So we look at, you'll see there's some coefficients here, tolerance and VIF, which are collinearity statistics. They seem to be reasonable for this model, but there's certain values that we look for in a model to say, okay, that indicates that there's a problem with collinearity. I'm not seeing anything here, but this is the way we would look for that. So it's just to point out that there's certain things that you need to look for when you're doing analysis. And then the other thing is we look for, when you're doing regression, outlier cases can also create problems. So there's one statistic here called the melanomas distance, which we look for outlier cases, extreme cases. So this maximum is very high. We would want to bring that down, and there's a way we could do that. I'm not going to explain it now, but normally when you're doing regression analysis, you need to look into these values. And then this table here is telling me that certain cases in the data set have got extreme residuals. So these residuals are all over 3. So what you would do is look to maybe removing these cases from the analysis, because they might be influencing the result in a negative way. So there's things that you need to look out for. These are some of the things that you need to look out for when you're doing regression analysis. Okay, this plot here should be more, this is the plot of standardized residuals, and you'd expect to see the line more on the, you'd want to see the data points more, they're not fitting that well to the line. They're not terrible, but you'd like to see them more sort of directly on the line rather than sort of having these sort of bends in the line. So that sort of suggests that there might be some need to adjust it or transform the data to get a better sort of standardized residual line. This doesn't look too bad. This is a fairly random pattern of data. So that's the kind of pattern that you want to see when you are doing regression. This one is also quite nicely random. This is also not too bad. This one's definitely got a sort of direct relationship, but that's looking at beginning salary and current salary. So we'd expect that to be there. So those are, yeah, so that's the regression. It's a very powerful technique because it allows us to predict what impact changing a an independent variable will have on a dependent variable. So in this case, you'd report the results here, but then that would also allow you to say that if we manage to increase education levels, we should be able to get our salary levels up. And also there's a gender, we know it's well established that there's a gender discrepancy in salaries, and this is showing that up. So it's kind of supporting what we know, and also indicating that there's still some work to be done in terms of making salaries more equal across the male and female. In this case, there's male and female in the sample. So this result would indicate that the problem persists in this data set or in this sample, and therefore, and then the analysis of that would say there needs to be some kind of intervention or some kind of steps taken to remedy that inequality if it's considered to be a major problem. Obviously, just increasing education might not lead to better salaries if the job market doesn't allow for the expansion of employment and salaries. But this is part of, this is speaking to the issue of the link between education level and salary, and sort of that particular relationship. So if you wanted to push that further, you might need to add more variables or analyze that in a broader economic context kind of thing. But that's what you can do with the regression. So that's it's a more sophisticated parametric test, which allows us to make estimates for multiple independent variables, and then those estimates allow us to make predictions about what the impact of changing one variable would be on the dependent variable, controlling for the other variables in the model. Okay. All right, so I know we're running out of time, so I'm going to just carry on. So reporting a regression, I've been through this, looked at that. Yeah, so again, if your student needs advice on how to write up a regression, there are examples in some texts. So for example, this is again from Palant in the chapter on linear regression. It's important to note that when you get to these more complex tests, there are different ways of writing up. So you can refer to the journal if you want to publish in a particular journal, for example. It might be worthwhile looking to see how other writers in that journal have written up their results to get an indication of what their preference is for how the data should be written up. Okay, so that could be, but this is just an example of how you would write up the regression. And then there's a text in the Morgan book. They do have a table where they indicate what statistics should be reported for particular tests. That's quite a useful summary table. And then there's different types of regression. I've already mentioned that for depending on what kind of outcome variable you have. All right, then the other kind of test is the non-parametric tests. So when you don't meet the assumptions for the parametric tests, there are a certain number of non-parametric tests that we can use. They're distribution free, so they don't rely on the normal distribution requirement that the parametric tests rely on. Some parametrics tests, but not all parametric tests have non-parametric equivalents. So for example, for independent samples t-test, there's the Mann-Whitney test. For ANOVA, there's the Krishkor-Wallace test. For Pearson's correlation, there's the Spearman's correlation. So there's, but there isn't the same range of non-parametric tests as parametric tests. These are some examples. We use them for the same reasons as we would use for parametric tests. This is a table from text, a book on non-parametric tests. So how do you choose which test to use? Again, it comes down to the nominal or categorical nature of the statistic that you are measuring. So of the variable. So if you're using nominal or categorical, or if you're using ordinal or ordered or interval variables, that will determine which kind of test you would use. So for example, and then you've got one sample, which is a single sample, a single group. You've got two sample, that would be more than two groups. And then you've got K sample, which would be three or more groups. And then you've got measures of association, which are your correlation coefficient will be there. So it's not about groups, that's more about variables that you want to correlate. So for example, if you've got two groups, and you just trying to find the Mann-Whitney test here. Where is it? It's not here. Wilcoxon's. It should be here. Mann-Whitney. Yeah, there's the Mann-Whitney test here. Yeah. So if you've got two groups, two groups, and you're testing a ordinal or ordered variable, you could use the Mann-Whitney test as a test to test the difference between those two groups. Yeah, if you've got three independent groups, then the Krishkal-Wallace would be the test that you use for the analysis. So that helps you, this table would help you decide which kind of test you would use for your non-parametric tests. This table by field also has non-parametric tests in the table where the answer is no here. There will be a non-parametric alternative, but there isn't always a non-parametric alternative for all the tests. So some of these tests here don't have non-parametric alternatives, for example. And the multiple outcome variables, if you've got multiple dependent variables, those tests, there aren't non-parametric tests for those for the parametric alternative. So for those, if you've got that design, you'd have to try and make sure that your sample meets the criteria for the parametric tests. Okay, so I'm just going to give one example of this because it's a slightly different test to the comparative test. This is measuring association. So there's a test called the chi-squared test, where if you're working with nominal variables and you want to use association, you want to measure association, we use something called the chi-squared statistic for that analysis. So I'm not going to go into detail about how it's calculated. The information is here. It's very technical. This explains how the statistic is derived. The point is that we do derive a statistic for that. We follow the same process. So we have a level of we have a hypothesis that we want to test. There's a level of significance that we set, and then we use a statistical test. We get a p-value, and then we accept or reject the hypothesis around those relationships. And then there's certain statistics that we look at to decide whether the statistic is going to be valid or not, or sort of useful or not. So I'm just going to do a quick example looking at the relationship between job category and sex of participant. Okay, so I'm going to go to SPSS. All right, so the crosstabs procedure actually occurs under descriptive statistics, but we can get a statistic from that from the crosstab. So it's a bit misleading. There is an inferential statistic that we can get from the crosstab under descriptive statistics. So it's but it's one of the reasons why it's here is because we get the table. It's more about the table than about the thing. So I'm going to put the sex of the employee in the column. I always put the independent variable in the column, and then I'm going to put the job category, which is where employment category here, in the rows. Okay, and then you can do it the other way around. Some of my colleagues do it the other way around, but I like to have the independent variable in the columns and the dependent variable in the rows. And your sex of your employee might influence your employment category. Your employment category doesn't determine the sex of the participant, so that's why I consider it that way around. Under statistics for this table, there's a chi-squared statistic. You can also do correlations if you have other kinds of variables. I'm also going to ask for the pi and Kramer's V, because that's an effect size measurement for the relationship. You also notice that there's kappa here, and that's used for rate of reliability. So if you were wanting to measure rate of reliability, that's where your kappa statistic could come from. So I'm not doing a nominal by interval, and I'm not going to use anything else here. So that's all I'm choosing there. Under cells, this is where you can decide what the table is going to look like. I'm only going to use column percentages. I want to see whether there's a difference in males and females in terms of their employment categories. When you calculate the chi-squared, it's based on the observed and expected counts. So if you wanted to see what the expected counts were, you can get that information as well, but we don't normally display that. It's useful for explaining how the coefficient is derived, but it's not something that we would normally look at. Yeah, and then there's you can run row and column total percentages as well, but I'm not going to do that now. Yeah, so that's and then the format is not really anything. Yeah, so I think that's it. You could also display a graph here, which would be a clustered bar graph. So I'll show you what that looks like, just so that if you wanted to generate a graph from the analysis, you can do that. Okay, so let's have a look at the results. I'm going to stop sharing that, getting confused with which window I'm in. Okay, this is the output. You should see an output window with a table on it. Can you see that output window?
Yes, we can.
Okay, good. Okay, so this is the percentage of males and females who are different categories. So if you look at the table here, you can see that 54% of females are clerical compared with 42% of the males. So a higher proportion of females are clerical to males. And then also for the office trainee, a very large percentage of females are office trainees compared with males, who are 18.2%. For security officers, 10.5% of the males are security compared with none of the female participants. And you've also got higher proportions of males as college trainee and exempt employee. And then small numbers, there's very small numbers of MBA trainee and technical, but pretty much all except one of those are male. So remember, this group had the higher salaries. So what this is showing is that there's a higher percentage of males in the better salary categories. So that's so on the face of it, just in terms of absolute terms, it looks like there's a significant, we'd say, a significant association between the sex of the employee and the employment category. But we need to do a statistic to confirm that that's the case. We can't just rely on the numbers. We need to actually measure more about these percentages and that's where the chi-squared statistic comes in. So this is the chi-squared statistic. We normally use the Pearson chi-squared. This is a very high value. There isn't a right or wrong value. But what's important is this p-value here is telling me that it's a significant result. So our p-value here is less than our alpha value that we'd set of 0.05. So if we were testing what we'd be saying here is that the null hypothesis will be that there's no association between sex of employee and employment category, or we'd be saying that the sex of employee is independent of the employment category. But based on this result here, we'd reject that null hypothesis and say that there is an association between sex of employee and job category. And the effect is that, or the result is that the female sample is more likely to be clerical or office trainee, and whereas the males are more likely to be security officers, college trainees, or one of these other categories. And that result is showing that. So it's confirming that there is a difference between the distribution of sex of employees different across the different employment categories. This here we've got 20. What some of the things we need to look out for is the minimum expected count and the percentage of cells with an expected count of less than 5. So if this is higher than 20%, or the minimum expected count is smaller than 1, then our test statistic might be a bit unreliable. But given the sample size here, I'm not too concerned about this being higher than 20%. I still think this is a significant result. And then the way of solving that problem would be to try and group some of these categories together to minimize the number of cells with a low expected count of 5. So partly why that's happening is over here in the table, because we've got so few people who are MBA trainees and technical. When we divide those between male and female, the expected count will be low, less than 5. So we've got at least 4 cells here, which would have an expected count of less than 5. And that's what's causing this 28% here. So if we could, we might group these together, but there might not be a good justification for doing that. It's not always that easy to make decisions about how to manipulate the data to get these statistics to fit into what we're looking for. But yeah, so, and then the Kramer's V is suggesting that it's a good effect size. So that difference is quite meaningful that we're seeing here. And again, moving beyond the kind of just displaying the result, is that you need to have a discussion about is this an appropriate distribution, or would you want to see a shift in the distribution for this particular sample? So that's where your analysis would sort of move beyond just describing what you're seeing here to kind of debating what the result means in terms of the sample. Okay, this is a bar chart of the distribution where you can see that the males are much more, there's many, I've used a count here. You can probably do a percentage as well. But it's showing that the males are more likely to be in these security officer, whereas the females are more likely to be office trainee or slightly more in clerical. The biggest difference here is, I think, for the office trainee, though, and then for these groups. This is fairly similar for clerical. It's the office trainee difference, and then these other categories where the difference is coming up. Okay, so that's an example of the chi-squared is a non-parametric technique, and that's there isn't a parametric alternative for the chi-squared. It's simply a non-parametric test because you're dealing with categorical variables for this analysis. Okay, I'm going to start ending up because we're getting towards 1 o'clock and you guys must be tired of hearing about statistics. Writing up the chi-squared, again, this is an example from Palant, where you can just say a chi-squared test for independence was indicated no significant association between, in the case between sex of participant and employment status. And then you give the chi-squared value with the 1 would be the degrees of freedom for the table, n is the sample size, and your p level and your effect size. In this case, they're using phi, but you could also use Kramer V. So it's just showing, in this case there was no significant association. For the example we've used, there would have been a significant association. Okay, so I've mentioned this already. There are alternatives for there are non-parametric alternatives for the paired samples t-test and these various other tests. I'm just going to, there isn't alternative for multiple regression. So there's some statistical tests where there's no non-parametric alternative. I just want to show you quickly where on the menu in SPSS you will find those tests. So here under Analyze, there's non-parametric tests here. I don't use the menu here. So under Legacy Dialogues, there's 2 independent samples, K independent samples. So this would be this would give you the Mann-Whitney test, which is the equivalent to the independent samples t-test. The K independent samples test would be your equivalent to the ANOVA. This would be the Krishkal-Wallace test. Yeah, so this is where you find your tests under the non-parametric tests in SPSS. I'm not going to run examples of those. Okay, I'm sure you've seen enough tests to last you a lifetime today. Okay, so just bear in mind that there are other kinds of tests as well. We've mentioned some. So if you want to test normal distribution, there's a test called Shapiro-Wilk or Kolmogorov-Smirnov. Those are tests for testing normal distributions. Then there's also the reliability testing, using Cronbach alpha, for example. Excuse me, you can measure inter-rater reliability using the kappa statistic. And I think I've mentioned, I think there's a paper that's been shared with you by Hallgren. So if you're doing inter-rater reliability, that's a very good paper to look at in terms of the kinds of tests, depending on the kind of measures that you're using for inter-rater reliability. Then validity, we've mentioned this before in the previous session. There's certain statistics that we can use to assess validity of our measures. And I gave you some examples of those in a previous session. There's also data reduction techniques which we use to reduce measures or cases. So we do exploratory factor analysis, confirmatory factor analysis, cluster analysis, discriminant analysis. Those put people into groups. Exploratory factor analysis puts variables into groups. Cluster analysis could put people into groups, or it might also be able to put variables into groups as well. Yeah, and then there's the effect size statistics. I've shown you some of those today. We use those to estimate the practical significance of a significant statistical result. Yeah, and then just in terms of helping students, there's Morgan, the book by Morgan, it should be Morgan et al., sorry, not just Morgan, From Numbers to Words. That's got chapters on different statistical procedures, and it includes a listing of statistics which you need to include if you're reporting on a specific test. So that's a good resource. Palant is an excellent book if you're starting out with something like SPSS. It covers a lot of different procedures, and it has examples of how to run the procedures. It has detail about the procedures, how to run them, and then also how to write up the results from the tests. Hancock and Muller is the reviewer's guide to quantitative methods. That's if you want a sort of high level of desiderata for several statistical procedures, that's a good text to use. And then there's also quite a few articles out there, published articles on people reporting on statistics in their disciplines, for example. So you might find an article, if you're working in the nursing discipline, you might find an article by somebody in the nursing discipline talking about the statistics that you can use that are mainly used in the discipline and what they are and how to report on them. So there's lots of resources out there. There's also fantastic web-based resources, so if you're looking for sometimes if I'm not sure how to run a procedure, I'll Google. And if I can't find it in one of my books or whatever, I'll Google online, and there will be somebody out there who's got something about it. Just be careful about the quality, though. Sometimes the quality of these things is not always that good. And then sometimes it's excellent and sometimes it's quite poor. I'll try and share a few resources with you which I think are quite good in terms of quality. And then obviously published work where statistics are used is a useful resource. So if people have published their work in journals, that will give you an indication of how to report on the results and how to write up. But just bear in mind that it might not be exactly the same as your design, so you might have to tweak things a bit. And then also, sometimes when people report in journals, they don't always report accurately. So it gets past the reviewers because the reviewers aren't statistical experts. So just be careful about the quality sometimes of the obviously the higher level the journal, the more likely it is to be accurate, but that's not always necessarily a sort of a given. Yeah, and I think when the student's writing up their results, they need to make sure that they they need to kind of state the hypothesis that they've been testing. If they're testing a hypothesis, they need to report on the statistical test used. They need to explain the type of test that's been used in the results, and they need to provide a concise summary of each relevant result, both positive and negative. So even when of the examples I've shown today,